Two galaxies can pass through each other and still tear themselves apart, not with impact but with gravity. In the black between stars, gas ignites, orbits unravel, and invisible dark matter drags the whole system into a new shape. When the Milky Way meets Andromeda, what survives the collision? Our stars, our sky, our black hole, or the story we tell ourselves about home? Out there, time does not hurry, yet whole galaxies can be rewritten before a single star ever knows it moved. What looks like a serene overlap becomes a forensic scene in motion, where every arc of light is a clue. This is a documentary about a collision you can't watch in real time, only reconstruct, frame by frame, from the debris it leaves behind. Because when two galaxies begin to share the same sky, they do not meet as solid objects. They meet as layered ecosystems, collisionless stars on inherited orbits, gas that can slam and cool, dust that can conceal, dark matter that can steer, and central black holes that can awaken. Our question is not whether a merger looks dramatic from afar, but what physics decides the outcome. Which components yield, which resist, and which quietly dictate the final shape long after the brightest fireworks fade. To answer that, we will follow the encounter as astronomers do, by tracing invisible forces through visible consequences. A faint bridge of starlight can mark a past close passage. A buried infrared glow can betray newborn clusters behind dust. A disturbed velocity field can reveal where angular momentum was stolen. We will step into the overlap region, where the first truly collisional material announces itself, and where shock fronts and turbulence redraw the map. We will watch gravity pull out ghostly tails and shells, structures so delicate they feel like accidents, yet so orderly they read like handwriting. And we will descend toward the centres, wherein flowing gas can build pressure, ignite compact starbursts, and raise the odds that a once quiet nucleus turns active. Somewhere in that crowded heart, two supermassive black holes begin a slow courtship that is both inevitable and difficult to witness. Yet the largest actor remains the one we cannot see directly. Dark matter does not shine, but it shapes the stage, sets the timing, and decides how stubbornly galaxies hold together when everything else is being stretched. For decades we inferred these events from faint smears on photographic plates, and from simulations that hinted at hidden order. Now, with the James Webb Space Telescope, infrared light cuts through dust and deep time, turning distant mergers into readable histories rather than mere spectacles. By the end, this will no longer be an abstract cosmic drama. It will be a forecast, drawn from patterns across the universe, of what kind of galaxy the Milky Way is becoming, and what kind of night sky could follow. One warning before we begin. The most important changes in a galaxy collision are rarely the ones that look like impact. They are the ones that look like inevitability. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We'll begin with the quiet approach, then move through first contact in gas, tidal sculpture, central starbursts, and the awakening of black holes. Finally, we'll step inside the Milky Way, Andromeda merger, to see how a future sky is written, in gravity, dust, and time. A galaxy collision sounds like impact, fire, and shattering light, as if the cosmos were made of glass. In reality, it begins as a quiet overlap of gravity fields, two invisible landscapes sliding into the same space. Two vast systems drift together for billions of years, and almost nothing ever touches in the ordinary sense. That is the paradox that frames this story, and it is why the opening act feels almost unreal. The biggest events in the universe can arrive without noise, because space is mostly emptiness and gravity works at a distance. When astrophysicists say collision, they rarely mean stars slamming together like billiard balls. They mean two gravitationally bound galaxies passing through the same volume of space, while their internal parts respond at different speeds. They mean tides that pull, torque, and rearrange orbits on enormous scales, like a slow wrench applied to a spinning disk. They mean gas clouds that compress, shock, and cool as they meet resistance, because gas has pressure and cannot pass through itself cleanly. They mean dark matter halos that interpenetrate without friction, yet steer everything else, an unseen scaffolding that dictates the dance. The word collision misleads because galaxies are mostly empty space, even where they look bright and crowded. A typical star is a few million kilometers wide, but the next star is light years away, separated by a gulf that dwarfs any stellar diameter. If you scale the Sun to a grain of sand, the nearest grain would be kilometers distant, and the city of grains would still feel sparse. In that geometry, direct star impacts are extraordinarily unlikely because the targets are tiny and the distances are huge. Even during a merger, most stars simply keep moving on altered paths, obeying gravity but never making contact. There is another reason stellar collisions are rare, and it is purely statistical. The cross-sectional area of a star is minuscule compared with the volume a galaxy occupies, so even a crowded passage is mostly near misses. Stars also move fast, often hundreds of kilometers per second, which shortens the time they spend close to any potential impact. The result is counterintuitive. Two galaxies can overlap visually, yet their stellar populations behave like interpenetrating swarms. Yet the encounter is still transformative, and the transformation is written into the shapes we can photograph. Gravity does not need contact to do damage, because it acts coherently across entire systems. Tidal forces can stretch a disk into long streams and shells, pulling out arcs that glow faintly against the dark. Orbits that were orderly can become scrambled and heated, turning a thin disk into a thicker, puffier structure. Gas that was stable can be driven inward, feeding bursts of star formation and changing a galaxy's future in a single episode. The collision is less like two rocks hitting and more like two weather systems colliding in slow motion, massive, fluid, and full of hidden currents. As the galaxies approach, the first changes are subtle and easy to miss in a single snapshot. Spiral arms can become asymmetric, and outer disks can warp like vinyl left in heat. Faint tidal tails can form long before the main bodies appear disturbed, because the outskirts are weakly bound and easily pulled away. Even the night sky inside each galaxy would change gradually, as starfields shift and the bright band of the Milky Way bends into unfamiliar contours. Our anchor timeline is close to home. The Milky Way is not alone, and it is not static, even if it feels permanent from one human lifetime to the next. It shares the local group with Andromeda, also called M31, and dozens of smaller companions, dwarf galaxies that orbit like moths around porch lights. The Milky Way and Andromeda are bound by gravity, already committed to an eventual merger, because their combined mass outweighs the expansion's local pull. The approach is not a guess. It is measured, refined, and tested against multiple lines of evidence. Andromeda is moving toward us with a radial speed of about 110 kilometers per second. That number is the line-of-sight component, read from the galaxy's spectral shift, where familiar absorption lines slide slightly toward the blue. It is a Doppler measurement, the same physics that changes the pitch of a passing siren, but applied to starlight spread into a spectrum. The sideways, tangential motion is harder to pin down because it requires tracking tiny angular changes across the sky. Even so, observations constrain it to be relatively small, and that constraint matters more than it sounds. With limited sideways motion, gravity wins, because there is not enough angular momentum to keep the galaxies safely circling. The two galaxies are on a converging trajectory through the local group, falling toward their shared center of mass. Their mutual pull is strengthened by their dark matter halos, which extend far beyond the visible disks and add most of the mass. In a sense, the collision begins in the dark, where the halos meet first and start reshaping the gravitational terrain. The timescale is long enough to feel abstract, but short enough to matter in the life of a star like the Sun. Models place the first close passage roughly 4 to 5 billion years from now, around the time the Sun itself will be evolving toward a hotter, more swollen phase. After that near miss, the galaxies will swing apart, then fall back together, because orbital energy is gradually drained. The final coalescence comes later, after repeated passages and the steady braking effect of dynamical friction. The end state is likely a single, larger remnant galaxy, with a new structure and a new history, sometimes nicknamed Milkomeda, though the physics is more important than the label. To understand what happens inside that collision, we need to define what a galaxy is in physical terms. It is not just a swarm of stars, and it is not a single rigid object moving as one. A spiral galaxy includes a rotating stellar disk, often with spiral arms shaped by density waves, regions where stars and gas bunch up as they orbit. It includes a central bulge of older stars with different orbital patterns, more randomized and less tied to a thin plane. It includes a halo of stars and globular clusters on wide, eccentric paths, many of them relics of earlier accretion events. It includes gas and dust threaded through the disk, and it includes a much larger environment beyond the visible light, where most of the baryons may actually reside. The interstellar medium is the galaxy's working fluid, and it is far from uniform. It includes atomic hydrogen that glows at radio wavelengths, molecular clouds where hydrogen pairs up and hides behind dust, and tiny grains of carbon and silicates that block and re-radiate starlight. It is cold in some places, hot in others, and turbulent almost everywhere, stirred by supernova shockwaves and stellar winds. It is where stars form, and where stellar feedback injects energy back into the galaxy, regulating how fast gas can turn into new suns. In a merger, this medium is the first component that can truly collide, because gas has pressure, and pressure changes everything. Inside molecular clouds, temperatures can drop to tens of Kelvin, and gravity can quietly take over. When a merger compresses these clouds, it can push them past a threshold where they fragment into dense cores. Those cores collapse, ignite, and produce clusters of massive, short-lived stars that flood their surroundings with ultraviolet light. The same event that triggers creation also plants the seeds of disruption, because those massive stars explode and churn the gas again. Beyond the disk lies the circumgalactic medium, a vast reservoir of thin gas that is easy to forget because it barely glows. It extends far outside the bright stellar body, connecting the galaxy to the larger cosmic web, where filaments of matter feed growth over cosmic time. The CGM can feed future star formation by slowly raining material inward, like a diffuse drizzle falling for billions of years. It can also be heated and stirred by outflows from stars and black holes, which can push gas outward and change its temperature and ionization. During a merger, the CGM becomes a mixing layer, and a shock front can propagate through it, converting orbital motion into heat. Then there is the dominant mass component, the one we cannot see directly but must include to make the motions make sense. Each galaxy sits inside a dark matter halo that outweighs the stars and gas, shaping rotation curves and stabilizing large-scale structure. Dark matter does not emit light, and it barely interacts with itself or normal matter except through gravity, so it passes through like a ghost. It forms the deep potential well that holds the visible galaxy together, and it sets the speed limits for orbits. In a collision, the halos overlap early, long before the bright disks meet, and their combined gravity begins to torque the galaxies. The invisible mass sets the choreography, even when the stage looks empty. At the center of each large galaxy is another key player, compact but consequential. The Milky Way hosts a supermassive black hole, Sagittarius A, with about 4 million solar masses, inferred from the rapid orbits of nearby stars. Andromeda hosts an even larger central black hole, and its nucleus shows evidence of a complex history. These objects are tiny compared to the galaxy, yet their influence can flare dramatically when fuel arrives. When gas is driven inward during a merger, accretion can ignite an active galactic nucleus, turning a quiet center into a beacon. That beacon can also be a regulator, shaping star formation through radiation pressure, jets, and winds that heat or expel gas. So what does the collision actually do if not smash stars together? It rearranges matter through gravity, and it transforms gas through hydrodynamics, which is the physics of fluids in motion. Tidal forces pull out long tails and bridges, stripping stars and gas into intergalactic space, where they can form faint streams that persist for billions of years. Dynamical friction transfers orbital energy into random motions, helping the galaxies sink together as their mass wakes gravitational disturbances in the surrounding halo. Shocks in the gas convert bulk motion into heat, then radiate it away, allowing the gas to cool and collapse again. Starbursts can follow, brief and intense compared to normal galactic life, lighting up the merger in ultraviolet and infrared. This is why the event is both gentle and violent, depending on what you choose to track. Individual stars mostly avoid contact, but entire stellar populations can be displaced, scattered, or flung into new orbits. The disks can thicken, warp, or dissolve into a more spheroidal remnant, because ordered rotation is converted into random motion. The central regions can become crowded with inflowing gas, raising pressure, and triggering rapid star formation in compact rings or clumps. Feedback from massive stars and supernovae can then blow cavities and drive winds, carving bubbles into the interstellar medium. The merger becomes a cycle of compression and expulsion, a pulse of creation followed by self-limiting blowback. Dark matter remains collisionless, but it is not irrelevant, and it is not passive. As halos interpenetrate, their combined gravity reshapes the orbits of stars and gas, and it can amplify instabilities in the disks. The halo merger can create a new, larger potential well with a different depth and shape, changing how tightly the remnant holds onto gas. Substructure in the halos can stir the disks and seed asymmetries, leaving ripples that persist after the obvious chaos fades. The final remnant's rotation and density profile depend on how those halos approached and mixed, including how much angular momentum was carried in. The invisible component leaves visible fingerprints, and astronomers learn to read them. Even the black holes have a merger story, and it unfolds on its own timetable. As the galaxy's centers sink, the black holes form a bound pair, orbiting inside a dense environment of stars and gas. Interactions with surrounding stars and gas can harden the binary, shrinking its orbit by transferring energy outward. Eventually, gravitational waves can carry away the final energy, allowing coalescence, a process predicted by general relativity, and now observed in smaller black hole mergers. That last step is far in the future for the Milky Way, Andromeda case, but it is part of the full arc. A galaxy collision can end with a black hole collision, and that ending sends its signature through space-time rather than light. The mystery is that we cannot watch any one merger from start to finish, no matter how patient we are. Human timescales are too short, and the process takes billions of years, so our observations are always partial. We build the narrative from snapshots across the universe, treating each interacting system as a different moment in a long sequence. Nearby, we see interacting pairs with tidal tails and disturbed disks, where individual star-forming regions can be mapped in detail. Farther away, we see earlier cosmic epochs when mergers were more common, because the universe was denser and galaxies were closer together. Each system is a frame in a long film we reconstruct after the fact, and the reconstruction is only as good as the evidence. This reconstruction has limits, and those limits shape what we think we know. Dust hides star formation in the very regions where mergers concentrate gas, so the brightest action can be buried behind opaque lanes. Optical light can show tidal features, but it can miss the buried engines in galactic centers, where accretion and starburst can be wrapped in thick dust. Even gas can be hard to trace when it is cold, diffuse, or heavily obscured, because different phases emit at different wavelengths. The evidence is incomplete, and the most important phases can be the hardest to observe, which is why the story keeps changing as instruments improve. In the past, astronomers relied on photographic plates and visible light surveys, and mergers were often recognized by their most dramatic silhouettes. Classic systems with long tidal tails became prototypes, teaching us what gravity can sculpt over hundreds of thousands of light years. As radio astronomy matured, hydrogen maps revealed that the disturbance extends beyond starlight, with gas tails stretching farther than the visible debris. Each new window added a layer, and each layer made the collision feel less like a single event and more like a multi-component transformation. A new detective has entered the case. The James Webb Space Telescope sees the universe in infrared, where dust becomes more transparent and where the cold and warm components of galaxies speak more clearly. It can detect the warm glow of dust heated by young stars, revealing star formation that optical telescopes underestimate or miss entirely. It can resolve faint, high redshift galaxies, where the early universe was crowded and chaotic, and where small systems merged rapidly to build larger ones. It can measure spectra that diagnose gas conditions, metallicity, and the presence of active nuclei, using emission lines as thermometers and chemical fingerprints. JWST does not just add detail, it changes which clues are visible at all, and that changes which stories are plausible. With JWST, mergers are no longer only dramatic shapes in nearby space, photographed like cosmic train wrecks. They become a statistical history of how galaxies assembled their mass, how quickly they formed stars, and how often they fed their central black holes. We can compare disturbed morphologies across time and connect them to bursts of star formation that show up strongly in infrared. We can search for dual-active nuclei, signaling black holes on a collision course, even when dust hides the cores at visible wavelengths. We can test whether the most massive galaxies grew by repeated mergers or by steadier accretion, and we can check those ideas against the chemistry of their gas. The local group becomes one example in a broader cosmic pattern, a nearby laboratory for processes that shaped the universe. Still, Our story begins with a quiet approach, because every spectacular merger starts with a long, silent fall. The Milky Way and Andromeda are already falling together through an almost empty gulf, and their motion is written in the light we receive today. Their outer halos likely overlap before their disks ever meet, blending dark matter and thin gas in a region with no obvious boundary. The first signs of the collision will not be a flash, but a subtle change in gravity's map. The kind of change only careful measurements reveal. Stars will feel new tides, and gas will begin to respond, first in the outskirts, and then deeper in. The whisper arrives long before the storm, and the storm is mostly a storm of gas. So we return to the central question. If stars almost never collide, what actually collides first, and what does impact mean in a place so empty? Which component feels contact, pressure, and shock when two galaxies overlap, and which component simply passes through, guided only by gravity? The answer points to the medium between stars, not the stars themselves, because gas can be compressed and heated in a way that stellar orbits cannot. To understand the merger's first real impact, we have to follow the gas, where friction and pressure finally make the encounter tangible. Next, we enter the interstellar medium, where motion becomes heat and heat becomes light, and where turbulence decides what collapses. We track how clouds compress, fragment, and ignite new generations of stars, then how those stars push back on their birthplaces. We watch how dust hides the action, and how infrared reveals it, turning obscured regions into readable maps of energy. The collision you cannot hear begins with a substance that can finally touch, and in that touch, the galaxies start to change their fate. If stars almost never collide, what actually collides first? The answer is gas, because gas has pressure, drag, and a memory of impact. In a merger, that memory is written as heat, turbulence, and radiation, signals that telescopes can catch long before any stellar crash could occur. A galaxy is not one substance moving as a unit. It is collisionless components, like stars and dark matter, embedded in a collisional medium of gas and dust. That distinction sounds abstract, yet it decides what can dissipate energy, what can change course quickly, and what simply coasts through the chaos. Stars behave like a swarm of nearly non-interacting particles, even when they share the same disk and spiral arms. They cross the overlap region on ballistic orbits, trading energy only through gravity's long reach. Even in a dense galactic disk, the typical distance between stars is so large that direct impacts are essentially impossible on merger timescales. The reason is scale, and it is almost unsettling when you do the arithmetic. A star is a few million kilometers across, yet the gaps between stars are measured in light years. Two galaxies can interpenetrate, and still their stellar populations mostly thread past each other like needles through fog. To picture it, imagine two vast clouds of gnats passing through each other in a stadium-sized volume. The gnats rarely touch, yet the overall swarm still responds to the stadium's gravitational contours. In galaxies, those contours are set by the combined mass of stars, gas, and an even stranger ingredient. Dark matter is even more ghost-like. It dominates the mass budget, yet it slips through with negligible self-collisions, shaping the potential without dissipating heat. Its presence is inferred from rotation curves, lensing, and dynamics, clues that emerged across the 20th century as astronomers realized visible matter could not hold galaxies together. Historically, the puzzle arrived in pieces rather than a single revelation. In the 1930s, Fritz Zwicky argued that galaxy clusters required unseen mass to stay bound. Decades later, Vera Rubin and collaborators mapped flat rotation curves, showing outer stars orbiting too fast for the visible disk alone. In a merger, dark matter halos interpenetrate first, long before the bright disks overlap. They are like two invisible landscapes sliding through each other, deepening and reshaping the gravitational valleys that everything else must traverse. The halos can exchange energy through gravitational interactions, but they cannot radiate it away as light. That matters because gravity can rearrange orbits without ever producing a flash. The dark matter's response is dynamical, expressed as changing velocity distributions and subtle shifts in the potential. If we could see it directly, we would watch two enormous translucent cocoons overlap and breathe through each other. Gas is different because it cannot ignore itself. When two gaseous disks interpenetrate, parcels of gas meet resistance, exchange momentum, and convert bulk motion into heat. Where stars cross like arrows, gas behaves like weather systems colliding, compressing, shearing, and rolling into new structures. This is the merger's first tangible contact. The encounter stops being purely gravitational and becomes hydrodynamic, with shocks, cooling, turbulence, and fragmentation. In other words, the collision becomes audible to the universe, not as sound, but as radiation across the spectrum. The interstellar medium is not one phase, it is a layered ecosystem, and each phase responds differently when galaxies begin to overlap. The same region can hold hot plasma, warm atomic gas, and cold molecular clouds, each with its own density, temperature, and characteristic timescales. Some gas is hot and ionized, filling bubbles and halos at millions of Kelvin. It is thin, pressure-supported, and it radiates in X-rays and high-energy lines. In visuals, it would appear as a faint ghostly glow around the galaxies, outlining superbubbles and extended halos that are otherwise invisible. This hot component is often created by supernovae and stellar winds, which inject energy into the surrounding medium. In a merger, it can also be stirred by large-scale shocks and by the mixing of circumgalactic gas reservoirs. Because it is diffuse, it cools slowly, and it can remain hot long after the first passage. Even its geometry carries information. Hot gas tends to trace chimneys and fountains, rising above disks where feedback has punched holes in the interstellar medium. During an interaction, those structures can tilt and warp, revealing where pressure gradients and tidal forcing are competing for control. Some gas is warm and neutral, closer to 10,000 Kelvin. It is more diffuse, often traced by atomic hydrogen, and it can be stirred into large flows. Radio maps of the 21-centimeter line reveal it as sprawling envelopes and tidal streams, sometimes extending far beyond the optical disks. That 21-centimeter line is a quiet but powerful messenger. It comes from a hyperfine transition in hydrogen, a subtle flip in the atom's energy state that can travel through dust with little attenuation. In merger visuals, it becomes a kind of cartography, showing where the galaxy's extended fuel has been stretched and displaced. This warm neutral medium is a kind of connective tissue. It can be compressed into denser phases, or heated and ionized into hotter ones depending on local conditions. During an interaction, it is easily pulled into bridges and tails because it is extended and loosely bound. Some gas is cold and molecular, shielded by dust and self-gravity. It lives at tens of Kelvin, clumps into clouds, and it is the direct reservoir for star formation. In imagery, it is the dark architecture of the merger, lanes, knots, and ridges that only appear when we observe in millimeter and infrared light. Cold molecular clouds are not smooth spheres drifting peacefully. They are structured, filamentary, and turbulent, with dense cores embedded inside more diffuse envelopes. When a merger compresses them, it does not merely squeeze a uniform sponge, it rearranges a fractal landscape of gas into new, denser configurations. That turbulence has a measurable signature. Molecular lines broaden when internal motions increase, and the line profiles can become asymmetric when multiple streams overlap along the same sight line. In a merger, those spectral fingerprints often look agitated, evidence that the gas is being stirred faster than it can settle. In normal spirals, molecular gas is a minority by volume but a majority by consequence. In mergers, it becomes the lever that turns orbital energy into new stars. That leverage comes from dissipation. Gas can lose energy through radiation, so it can settle, pile up, and reach the densities gravity requires. Astronomers trace dense molecular gas indirectly. Carbon monoxide lines map where H2 hides, and dust emission reveals where starlight is being absorbed and reprocessed. Molecular hydrogen is abundant but hard to see at cold temperatures, so observers rely on these proxies like fingerprints at a crime scene. CO is bright in the millimeter band, and its rotational transitions can be mapped with radio interferometers. The intensity and line widths tell us where gas is concentrated and how violently it is moving. In a merger, CO maps often light up the overlap region like a bruised seam, marking where the disks are truly colliding. Those maps also reveal structure within the seam. Instead of a single blob, observers often find clumps, filaments, and velocity gradients that hint at converging flows. The overlap region can behave like a compressed interface, where gas from both galaxies is forced into shared, unstable orbits. Dust emission adds another layer of truth. Tiny grains absorb ultraviolet and optical photons, heat up, and glow in the infrared. with a spectrum that reveals temperature and optical depth. When we overlay dust maps on optical images, we often discover that the quiet core is actually the most active region. Dust is also a record keeper of environment. Grain sizes and compositions shift under strong radiation fields, and aromatic features can brighten where ultraviolet photons excite complex molecules. In a merger, infrared spectra become a diagnostic palette, telling us where the energy is concentrated and how deeply it's buried. Those traces matter because the collision's brightest phase can be invisible in optical light. The gas that forms stars is often wrapped in dust that blocks UV, so the merger can look modest in visible images, while its true power is blazing in wavelengths our eyes cannot see. When the disks overlap, relative velocities can reach hundreds of kilometers per second. Gas streams that would pass through as stars instead collide and shock. The difference is not subtle. A star can traverse the overlap region with little more than a gravitational nudge, while a gas cloud can be abruptly slowed and heated. A shock is a sudden jump in density, pressure, and temperature. It is the fluid's way of enforcing causality when supersonic flows meet. In slow motion, you would see sharp fronts sweep through the gas, like ripples in a storm cloud, except the ripples are compressions that can trigger collapse. In physical terms, the shock converts ordered motion into random motion. The gas behind the front is hotter, denser, and often more ionized, and it can emit strongly in diagnostic lines. The shock strength depends on Mach number, how fast the flow is compared with the local sound speed. The immediate effect is heating. Kinetic energy becomes thermal energy, and the gas can briefly reach temperatures where atoms and ions radiate strongly. In spectral terms, lines brighten, ionization states shift, and the cooling budget changes as different elements take turns carrying energy away. But heating is only half the story. Gas can cool, and cooling changes the outcome because it lets compressed material stay compressed. Without cooling, the shocked gas would rebound, expanding like a spring and erasing the density enhancement that star formation needs. Radiative cooling happens through line emission from atoms and ions, and through dust grains that absorb energy and re-radiate it in infrared. The details depend on density, metallicity, and ionization. Metals, elements heavier than helium, provide many efficient line transitions, so enriched gas can cool far faster than pristine material. Cooling is also sensitive to how quickly photons can escape. In dense, dusty regions, radiation can be trapped and reprocessed, changing the effective cooling pathway. Yet even then, the system finds a way to shed energy, often by shifting the emission into infrared bands where dust becomes a luminous outlet. If cooling is efficient, the post-shock gas loses pressure support. Density rises, turbulence cascades, and the gas becomes prone to gravitational collapse. What began as a large-scale orbital encounter turns into a local contest between gravity, pressure, and chaotic motion. This is how a graceful gravitational encounter becomes luminous. The collision does not need stars to hit, because gas can dissipate energy and pile up. The merger's light, in many cases, is the glow of dissipated motion, orbital energy converted into radiation through countless microscopic interactions. Compression also changes chemistry. As gas densifies and shields itself, molecules survive longer, and cooling channels multiply, helping clouds fragment into smaller pieces. Dust grains provide surfaces where molecules can form, and shielding reduces destructive ultraviolet radiation, so the molecular fraction can rise quickly in compressed regions. In the coldest pockets, carbon shifts into CO, and hydrogen remains locked in H2. These molecules are not just passive tracers, they are part of the cooling machinery that allows gas to reach the low temperatures needed for collapse. The chemistry, the radiation field, and the density all evolve together, tightly coupled. There is a quiet question embedded here. How quickly can a region change identity, from warm atomic gas to cold molecular gas, when the merger forces it into a denser, darker state? The answer depends on shielding, dust abundance, and time, and mergers often supply all three in abundance. Turbulence is the merger's hidden engine. Shocks inject chaotic motions, and those motions both support clouds and create dense filaments where collapse can start. Turbulence can delay star formation by stirring gas, yet it can also accelerate it by producing rare, extreme compressions, dense knots where gravity suddenly dominates. Observers see this as a two-faced medium. The average cloud may look overpressurized and stable, while tiny pockets collapse rapidly inside it. In a merger, that contrast can sharpen, because the driving scale of turbulence becomes galactic, yet the collapse scale remains stubbornly local. In the densest pockets, gravity wins. Cores collapse, protostars ignite, and clusters form quickly compared with the merger's orbital timescale. A galaxy merger unfolds over hundreds of millions of years, but a cluster can assemble in a few million, turning a transient compression into a long-lived stellar population. The result is a starburst, a temporary phase where star formation rates rise far above the isolated galaxy baseline. It is intense, compact, and often short-lived. The burst can be concentrated in the central kiloparsec, or spread across the overlap region depending on geometry and gas distribution. A starburst is also a change in how the galaxy looks at every wavelength. Ultraviolet pinpoints appear where the dust is thin, while infrared swells where the dust is thick. In a wide shot, the system can seem calm, yet in the thermal glow it looks like a furnace with multiple vents. Historically, the link between interactions and starbursts became clearer as infrared astronomy matured. Early optical surveys saw peculiar morphologies, but the true energy output often appeared only when detectors could measure the far infrared glow. That shift in capability changed the narrative from distorted galaxies to engines of hidden star formation. The story accelerated with all-sky infrared surveys. When ERAS revealed galaxies whose luminosity emerged mostly in the infrared, mergers moved from curiosity to central engine. Many of the brightest infrared systems turned out to be interacting pairs, their cores wrapped in dust that optical images could not penetrate. Starbursts are not arbitrary. They follow an empirical rule, the Kennicutt-Schmidt relation, linking star formation surface density to gas surface density. It is a statistical law, not a strict recipe, yet it captures a deep truth. More gas per area usually means more star formation per area. The relation is often written as a power law, and the exponent encodes how rapidly star formation accelerates with density. In plain language, doubling the gas surface density tends to more than double the star formation surface density. Mergers exploit that nonlinearity by forcing gas into denser configurations. In quiet disks, the relation reflects how often gas reaches high density and how efficiently it turns into stars. In mergers, the same relation is pushed into a new regime. Gas is driven into denser states more frequently, and the fraction of mass in gravitationally unstable structures rises. The collision drives gas to higher surface densities, and it increases the fraction of gas in dense star-forming states. The starburst is the statistical consequence of that shift. Seen from afar, it can look like a sudden ignition, but physically it is the culmination of compression, cooling, and angular momentum loss. Some of the boost comes from direct disk overlap and shocks. Another major boost comes from torques that rearrange angular momentum inside each galaxy. Gravity does not merely pull the galaxies together, it twists their internal structures, creating pathways for gas to move inward. Tidal forces do not only stretch stars into tails, they also create non-axis symmetric structures, like bars and lopsided arms, that act like gravitational wrenches on gas. In visuals, a bar is a bright, elongated spine across a disk, and along its edges dust lanes often appear as dark, razor-thin streaks. Those dust lanes are more than decoration. They mark where gas is crowding into shocks along the bar's leading edges, losing energy and angular momentum as it goes. In a time-lapse, the lanes seem to feed the center, channeling material inward like converging currents. Gas feels those wrenches because it can dissipate. It shocks along dust lanes, loses angular momentum and spirals inward instead of staying on near-circular orbits. The process is subtle in a single snapshot, yet unmistakable in motion. Gas streams converge, collide, and settle into tighter orbits. This inflow can be dramatic. Large fractions of a galaxy's cold gas can be funneled into the central kiloparsec over tens to hundreds of millions of years. The inflow is not a smooth river. It is a sequence of episodes, often strongest near pericenter passages when tidal forcing peaks. Inflow also changes the central environment in ways that amplify themselves. As gas piles up, pressure rises, cloud collision rates increase, and the medium becomes more strongly self-gravitating. The center becomes not just denser, but more efficient at converting disturbance into collapse. The center then becomes a pressure cooker. High densities raise collision rates between clouds, increase cooling, and build the conditions for nuclear starbursts. In the nucleus, the gas surface density can climb so high that the region becomes optically thick, turning the core into a buried furnace whose light escapes mostly in infrared. The same inflow can feed a central black hole. Accretion is not guaranteed, but mergers make fuel delivery easier by removing the angular momentum barrier. The black hole's influence is tiny on galactic scales, yet in the inner parsecs it can dominate, converting in falling mass into radiation with extraordinary efficiency. This is where the documentary's central question sharpens. A merger reshapes galaxies by redistributing energy and angular momentum, and gas is the component that can shed both. Stars can be flung into tails and shells, but they keep most of their orbital energy, while gas can radiate it away and settle. Dust is the complicating witness. The same grains that help molecules survive also hide the newborn stars, absorbing UV and optical photons before they escape. Dust lanes can look like mere silhouettes, yet they are often the densest structures in the frame, ribbons of material thick enough to reshape what we think we are seeing. Absorbed energy is not lost. Dust re-radiates it in infrared, turning buried star formation into a thermal glow that can dominate a merging system's luminosity. The spectrum shifts from starlight to heat, from sharp blue clusters to a red diffuse radiance that speaks of embedded activity. This is why many mergers become luminous infrared galaxies. Lurgs and U-lurgs are not necessarily forming exotic stars, but they are forming many stars behind thick dust. Their luminosity is a calorimeter reading, an accounting of energy absorbed and re-emitted rather than a direct view of the sources. In the most extreme cases, the infrared output can rival that of a quasar, even when the optical image looks muted. The system's power is real, but it is reprocessed, emerging as warm dust continuum and bright mid-infrared features. The veil becomes the message, if we know how to read it. Infrared observations change the census. Optical surveys can underestimate star formation in mergers because they see the unobscured outskirts and miss the buried core. This mismatch once led to underappreciating how transformative mergers can be, particularly in dusty phases where the most intense star formation is hidden. JWST's mid-infrared capabilities push deeper into that hidden phase. Warm dust, aromatic features, and fine structure lines reveal where energy is being injected and how dense the gas is. In a JWST view, the core can bloom with structure, bright knots, filaments, and gradients that trace heating and obscuration together. It is not just that JST sees through dust better. Its angular resolution also matters, because it can separate neighbouring knots that older infrared telescopes blurred together. What once looked like a single glowing core can resolve into multiple embedded clusters, each at a different stage of emergence. JWST also helps separate power sources. Spectral diagnostics can distinguish starburst heating from active nucleus heating, even when both are embedded in dust. Line ratios, continuum shapes, and features associated with complex hydrocarbons can indicate whether massive stars or an accreting black hole dominates the energy budget. Early interaction leaves signatures before final coalescence. Some are direct, and some are statistical, but together they mark the moment gas begins to collide. The galaxies may still look like two distinct spirals, yet their interstellar media are already exchanging momentum and rewriting their internal structure. In less obscured regions, HAR and UV brighten as massive stars form and ionize their surroundings. These traces are fast, fading within tens of millions of years. They are the fireworks of star formation, brilliant, brief, and biased toward regions where dust is not too thick. The HAR glow is especially revealing in motion. It outlines ionized bubbles and expanding shells, showing where young stars are pushing back on their birth clouds. In interacting systems, those bubbles can overlap and merge, forming superbubbles that hint at clustered, synchronized star formation. In obscured regions, the core brightens in infrared. The luminosity can rise while optical images still look only mildly disturbed. That contrast can be unsettling. The visible morphology suggests a gentle interaction, while the infrared reveals an energetic event unfolding behind a veil. Gas kinematics become messy. Velocity fields show streaming motions, shocks, and multiple components, revealing that the gas is no longer following simple rotation. Spectral lines broaden, split, and skew, as if the galaxy's orderly traffic has turned into a multi-lane interchange with sudden stops and collisions. With integral field spectroscopy, the disorder becomes a map. One pixel shows rotation, the next shows inflow, and another shows outflow, all within the same region. The merger writes its dynamics into the line profiles, and the profiles tell us where energy is being dissipated most efficiently. Dust lanes become warped and overlapping. They trace where gas is being compressed and where inflows are channeling material toward the center. In close-up visuals, these lanes can look like braided rivers, converging toward the nucleus, with bright star-forming knots appearing at bends and intersections. Bridges of material can connect the galaxies. These bridges carry gas and dust across the gap, and they can host their own pockets of star formation. The bridge is not just debris, it is a conduit, a temporary structure where gravity and dissipation collaborate to move matter between systems. The antennae galaxies are a nearby template for this stage. Their overlap region is rich in molecular gas and young clusters, while dust hides much of the most intense activity. In optical light, the scene is dramatic. Two distorted disks with sweeping tidal tails, yet the true collision front is traced by CO and infrared emission. In a multi-wavelength sequence, the antenna almost change personalities. Optical images emphasize star clusters and tidal sculpture, while radio and infrared reveal the heavy, cold machinery underneath. The overlap region becomes the protagonist, a crowded interface where gas is being forced into new gravitational bargains. If we could fly through that overlap region, we would pass through a labyrinth of clouds. Some would be shredded by shear, others compressed into filaments, and a few would collapse into clusters that will outlive the merger itself. The antennae remind us that first contact is not a single instant, but a distributed zone of interaction. Not every merger produces the same outcome. Gas fraction, orbital geometry, and feedback strength determine whether the starburst is widespread, nuclear, or surprisingly modest. A gas-rich, head-on encounter can ignite a powerful burst, while a gas-poor or glancing passage may produce only localized enhancements. Geometry matters in a very practical sense. If the disks meet edge-on, shocks can be concentrated into narrow lanes, while face-on, overlaps can spread compression across broad regions. Even the orientation of bars and spiral arms can decide where inflows stall and where they accelerate. Feedback begins early. Massive stars drive winds, radiation pressure, and supernova shocks that can disrupt clouds, regulate efficiency, and launch outflows from the densest regions. Feedback is not merely destruction, it is also a sculptor, carving cavities, compressing neighboring gas, and setting the rhythm of subsequent star formation. Supernovae, in particular, act like delayed detonations. They arrive after the most massive stars have lived briefly and died, injecting momentum and energy into gas that has already been compressed by the merger. The result can be a layered medium, with hot cavities inside colder, denser walls. Even so, feedback does not erase the inflow immediately. The merger keeps applying torques, and repeated compression episodes can sustain elevated star formation over multiple passages. The system becomes a tug-of-war between inflow and expulsion, between gravity's insistence and feedback's resistance. The key is dissipation. Stars and dark matter can be rearranged, but they cannot radiate away orbital energy, while gas can cool and settle into new configurations. This single physical difference explains why gas concentrates, why it shocks, and why it can transform an interaction into a luminous event. That difference explains why gas often concentrates toward the center, while stars spread into tails and shells. The collisionless components remember the encounter as altered orbits. Their memory is geometric, written in arcs and streams that can persist for billions of years. Gas remembers it as heat and light. It shocks, cools, fragments, and turns into stars, and that conversion locks the merger's energy into a new stellar population. Once gas becomes stars, the dissipation stops, and the newly formed clusters carry the imprint of the merger's conditions: density, pressure, and turbulence. Our anchor timeline stays close to home. When the Milky Way and Andromeda first pass, their gas will meet before their stars ever notice contact. The first interaction will likely occur in the extended gaseous halos, where tenuous plasma and warm gas begin to mix and shock. Their circumgalactic gas will mix and shock on large scales. Their disks will later overlap, and the densest clouds will feel the strongest compression. Even if the stellar disks appear to glide past each other, the gas will be exchanging momentum, heating, and cooling in a complex evolving interface. It is worth pausing on the strangeness of that future scene. The night sky would not show stars colliding like sparks, because that is not how galaxies touch. The true first contact would be a slow, invisible friction. detectable only through the radiation of heated gas and dust. The future details depend on how much cold gas remains by then. Even with less fuel, the physics stays the same, because dissipation always makes gas the first responder. The question becomes not whether shocks occur, but how much dense gas is available to turn those shocks into a starburst. This chapter's mystery is that the brightest phase can be hidden. The collision announces itself not with a bang in visible light, but with heat re-radiated by dust. It is a reminder that the universe often tells its most energetic stories in wavelengths we must learn to translate. So the first sparks of a galaxy collision are not stellar impacts. They are shocks in a diffuse medium, followed by cooling that lets gravity take hold locally. The drama begins in gas that is nearly invisible, then becomes undeniable as it condenses fragments and lights up its surroundings. Gas makes the first sparks, but gravity shapes the entire stage. Next, we follow the tides, the invisible hands that stretch galaxies into new forms. Gas makes the first sparks. Gravity decides what those sparks become and what the stars remember. When two galaxies approach, the scene can look calm at first. Two luminous islands drifting in a dark ocean, their spiral arms still neatly wound. Yet the real encounter begins before any bright disks overlap, because gravity reaches far beyond starlight and well beyond what most images first reveal. A galaxy is not pulled as one rigid body during an encounter, and that detail is everything for what follows. Each star and cloud feels gravity from both galaxies, and the difference across the system is the tide. Tidal forces are differential gravity, and that phrase matters because it explains the stretching without invoking any collisions. The near side of a galaxy is tugged harder than the far side, so the whole structure elongates, twists, and can be partially unbound. In a simple sense, the galaxy is being pulled apart because gravity is not uniform across it, even if the overall pull points inward. The larger the object, the larger the difference in pull from one side to the other, and a disk tens of thousands of light years wide is a perfect canvas. On Earth, tides lift oceans because the moon's pull varies across the planet, and the gradient is small but persistent. The near ocean bulges toward the moon, while the far side bulges because Earth is pulled more than that water, leaving it slightly behind. In galaxies, the same idea acts on disks where the water is stars and gas, and where the timescales are measured in hundreds of millions of years. Nothing splashes, but orbits subtly shift, and those shifts can accumulate into visible structures that seem impossibly delicate. The strongest tides arrive at close approach, when the gravitational gradient becomes steep, and the encounter's geometry becomes decisive. Astronomers call that moment peri-enter, when the separation is smallest, and the tidal field changes fastest. Peri-enter is not just a point on a diagram, because the tidal field can swing in direction as well as strength. It is a brief interval when the outer parts of a disk can be jolted out of equilibrium, and when small differences in timing can echo for billions of years. At pericenter, the outer disk is the first to yield, because it is only loosely bound and already close to escape. Stars there orbit more slowly and sit in a shallower part of the galaxy's potential well, where a modest tidal impulse can matter. A companion's pull can add to a star's motion rather than cancelling it, and that alignment can lift the orbit into a long arc. Gas in the outskirts is even more responsive, because it can compress, shock, and cool, turning a gentle tug into a dense star-forming ridge. Those arcs become tidal tails and stellar streams, and their scale can be startling when the camera pulls back. They can extend hundreds of thousands of light years, and they often curve like brushstrokes that fade into darkness. In deep images, a tail can look like a ribbon of frost, thin and luminous near the disk, then dissolving into a granular mist of unresolved stars. The remarkable part is their longevity, because even as the parent galaxies evolve, these features can remain coherent for billions of years. A tail is not a simple spray of debris, and it is not made by stars colliding, because direct stellar impacts are essentially non-existent. It is a structured response of many orbits, shifted by torques and then sheared by differential rotation. Each star continues to follow gravity, but the encounter changes its energy and angular momentum slightly, like a tiny edit to a long-running trajectory. Those small changes are correlated across the disk, so the result is a collective pattern rather than random scattering. Differential rotation then does its quiet work, and it does it with mathematical inevitability. Inner disk material orbits faster than outer material, so any disturbance is stretched into a long, thin feature that can wrap and unwind. The tail shape becomes a record of how the disk rotated at the moment of impact, including how quickly the rotation curve rose and flattened. In that sense, tidal debris is a kind of fossilized kinematics, geometry preserved in faint light, waiting for us to measure it. Some material is pulled outward and then falls back, returning on elongated orbits that can wrap around the remnant like a loose scarf. Some is flung onto loosely bound trajectories, populating the halo and intergalactic space with diffuse, low-surface brightness light that blends into the background. That faint glow is easy to miss because it can be far dimmer than the night sky seen from Earth, and it is vulnerable to instrumental scattered light. Yet it represents real mass, redistributed by a single gravitational encounter, and it changes where future stars can form. A second signature often forms at the same time, and it can be even more evocative in motion. A tidal bridge can connect the galaxies, a temporary corridor where gravity draws material across the gap and holds it there. In images, bridges can look like a thread pulled taut between two spinning wheels, with dust lanes braided through the light. They can also appear clumpy, because gas within them can fragment, collapse, and form stars in pockets, where the density briefly peaks. Bridges are not only optical curiosities, and they are not merely decorative scars. They can carry gas that later fuels star formation, and they can seed new dwarf-like condensations in the debris. In some systems, those condensations become tidal dwarf galaxies, bound objects formed from recycled disk material rather than pristine primordial halos. That possibility is one reason bridges matter for galaxy evolution, because they show that interactions can both destroy and create. They are not just traces of violence, but channels of redistribution, and the difference depends on how gravity and gas cooperate. Tails and bridges are the visible handwriting of orbital geometry, and the handwriting is surprisingly sensitive to small changes. Change the approach angle, the spin direction, or the closest distance, and the debris field can shift from elegant symmetry to chaotic asymmetry. The same two galaxies can produce very different structures, depending on how they meet and how their disks are oriented at first contact. This is why astronomers treat morphology as a clue rather than a decoration, because the shape is a constraint on the orbit. The key distinction is prograde versus retrograde, and it is really a statement about resonance and timing. In a prograde encounter, the companion's orbit aligns with the disk's rotation, and resonances amplify the tidal response over many internal orbits. The disk's stars are already moving in the same sense as the tidal forcing, so the perturbation can act coherently rather than cancelling itself. It is like pushing a swing at the right time, where small pushes accumulate into a large amplitude. The energy transfer becomes efficient, and the disk can respond dramatically. Prograde passages tend to produce long, bright tails, and the reason is almost mechanical. The disk's rotation helps fling material outward, like a moving walkway that adds speed at the edge just when the tide tugs. Stars near the outer rim can be nudged onto trajectories that extend far beyond the original disk, and the tail can remain narrow at first. Gas follows too, and because gas can compress, tails can host knots of star formation that light up in blue and ultraviolet. In ultraviolet images, those knots can shine like beads on a string, marking where shocks and compression crossed a threshold. In retrograde encounters, the disk spins against the orbital motion, and the same forcing is less resonant. Tails are shorter and the disk can look less shredded, even when the masses are similar and the pericenter is close. The perturbation still acts, but it does not catch the disk's rotation in the same way, so coherence is harder to sustain. Instead of a long ribbon, the response may be a thickened disk, subtle warps, or a more symmetric disturbance that hides its violence. The difference is not about strength alone, because it is about timing and phase alignment. Inclination matters as much as spin direction, because disks are three-dimensional structures with thickness, vertical motions, and pre-existing ahemetries. Tilted disks respond in 3 dimensions, producing warps, polar streams, and debris planes that do not match either original disk. A disk can be bent like a record left in the sun, one side lifted and the other depressed, with the line of nodes slowly precessing. In extreme cases, material can be thrown into loops that orbit nearly perpendicular to the main plane, and those loops can persist as faint tilted rings. Impact parameter shapes the violence, and it determines whether the encounter is a grazing pass or a plunging strike. A near head-on passage drives strong tides and strong shocks, while a wider miss can still torque the outskirts into a symmetry. The impact parameter is essentially the encounter's missed distance, and it sets how concentrated the tidal field becomes near pericenter. A close, plunging path can punch through a disk and excite strong radial motions, while a more distant pass can still pull out tails without fully dismantling the spiral pattern. Relative velocity sets the interaction time, and time is a hidden ingredient in tidal sculpting that is easy to overlook. A fast flyby delivers a brief impulse, while a slower passage allows tides to act longer and extract more material, especially from the outskirts. In the impulse limit, stars receive a quick change in velocity, then continue on altered orbits with little time to reorganize collectively. In slower encounters, the perturbation can act more adiabatically, letting the disk respond as a coupled system of orbits and waves. The same mass can therefore produce different outcomes, simply by changing speed and duration. Mass ratio decides which galaxy is transformed and which one becomes the sculptor in the encounter's first act. In a major merger, both disks are strongly disturbed, and the remnant can lose its thin disk identity as ordered rotation is scrambled. The encounter can heat the stellar component, build a spheroid-like distribution, and leave only a faint memory of spiral structure in kinematic subcomponents. In a minor merger, the primary can survive as a disk, but it is heated and thickened, and its outer regions can be warped. The smaller satellite is stripped, stretched, and often dissolved into streams, leaving behind a luminous trace of its orbit. The debris is not random, and its order is what makes it scientifically valuable rather than merely photogenic. Stellar streams trace the satellite's orbit, and their curvature and width encode the gravitational potential they move through, including how flattened or triaxial the halo might be. A narrow cold stream suggests gentle tidal stripping and a relatively smooth potential, meaning the stars retain similar energies and phases. A broader, puffed stream can indicate stronger perturbations, repeated heating by substructure, or a more chaotic accretion history. Even the stream's internal clumpiness can carry information, because gaps and wiggles may mark past encounters with unseen mass. That is why streams are time capsules and why their faintness is worth the effort. They map past accretion events, revealing how a galaxy grew by swallowing smaller companions over cosmic time. The idea that galaxies assemble hierarchically has deep roots in modern cosmology, and it was sharpened by decades of simulations that showed halos built from many mergers. When we see a stream, we are seeing an event that happened long before humans existed, and we are seeing it in a form that still remembers its initial conditions. The stars are old, but the structure is younger than the galaxy itself, and that contrast is part of the mystery. Sometimes the debris does not form a long tail, and instead it forms shells, faint ripples that look like nested arcs around a galaxy's outskirts. In photographs, shells can resemble the rings of a tree trunk, except they are made of starlight, and they often appear offset like a pattern that has slipped. They are often subtle, visible only when the galaxy's bright core is carefully subtracted, and the background is modelled with patience. Yet once seen, they look strangely geometric, as if drawn with a compass, and they invite a question. What kind of collision makes something so orderly out of something so disruptive? Shells often arise in minor mergers on radial orbits, where the satellite plunges in and out like a thrown stone. Stars from the disrupted satellite pile up near turning points, where their radial speed briefly drops and their trajectories linger. Those turning points are apocenters, the farthest reaches of their oscillations in the host's potential, and they act like traffic jams in phase space. When many stars reach apocenter at similar times, their density increases and the light sharpens at an edge. The result is a caustic formed by orbital crowding, a bright boundary created without any physical wall. This is phase wrapping, and it is one of the cleanest demonstrations that galaxies are collisionless systems. As stripped stars oscillate in and out, their orbital phases spread, and density caustics appear as sharp-edged shells that can interleave on opposite sides. The shells can move outward over time as different energy groups reach their turning points, so the pattern evolves even as the galaxy seems still. In that way, a shell system can act like a clock, because spacing and sharpness hint at when the merger occurred and how the host potential is shaped. The clock is imperfect, but it is readable, and it turns faint light into chronology. Rings can also appear, especially in near head-on encounters, where the geometry forces a disk-wide response. A density wave can propagate outward through a disk, compressing gas into a circular star-forming pattern that looks like a luminous ripple. The wave is not a rigid ring of material moving outward, because stars and gas pass through and briefly crowd, then continue on. It is a pattern, like a ripple on a pond, and its speed depends on the disk's mass distribution and rotation. Gas responds strongly because it can shock and cool, turning compression into star formation, and the ring can glow with young clusters and ionized nebulae. But here's what almost no one tells you when they show you these breathtaking photographs. Every tail, every shell, every glowing ring you've ever seen isn't a different kind of event at all. They're all the same thing in disguise, the same invisible hand, caught in different moments, wearing different masks. And once you learn to read them, these frozen snapshots reveal something we'll come back to later in this video. A way to reconstruct a collision that ended long before humans existed. Almost like reading a crime scene billions of years after the fact. For now, look closer at what these shapes really are. These features are not separate stories, even if they look different in photographs. They are different outcomes of the same physics, filtered through geometry, mass, and angular momentum, and then written in materials that respond differently. A tail, a bridge, a shell, and a ring are all ways gravity expresses differential pull and orbital response, and each one is a clue to the initial conditions. The variety is the point, because it tells us that the encounter's details matter, and that galaxies are not simple test particles. They are extended, rotating systems with memory, and the encounter edits that memory in visible ways. Angular momentum is the merger's currency, and it is exchanged rather than destroyed, even when the shapes look chaotic. Tides and torques transfer it between orbit and internal rotation, redistributing where matter can stably live and how it can move. A torque is a gravitational twist, a force that changes rotational motion, and it becomes powerful when a galaxy is no longer symmetric. In encounters, non-axis symmetric structures like bars and spirals become conduits for that exchange, and they can persist as the system evolves. The orbit can lose angular momentum while internal components gain or shed it, and that trade determines what falls inward and what is flung outward. In the disks, torques can drive bars and lopsided modes, and those asymmetries can persist long after the first pass, like a bruise that does not fade. A bar is more than a visual feature, because it is a rotating gravitational potential that can trap or scatter orbits and reorganize the disk. Once a bar forms, it can torque the gas, helping it lose angular momentum and drift inward along dust lanes where shocks compress it. The inflow can be slow at first, then accelerate when shocks develop along bar-driven lanes, and the gas begins to pile up in the inner kiloparsec. In the outskirts, the same torques can lift stars outward, and the contrast is one of the merger's signatures. The encounter can simultaneously feed the center with gas and empty the edges into tails, and both flows are powered by the same gravitational transaction. The galaxy becomes more concentrated in its inner regions, while its outer parts are flung into low-density structures that can survive as streams. The center grows denser, and the halo grows more extended. Two consequences of one exchange, written on very different scales. As the two galaxies swing past, the gravitational potential changes rapidly, especially near coalescence when the cores approach and the mass distribution reconfigures. For stars, that time-dependent potential can scramble orbital energies in a process called violent relaxation, a term coined in the early days of modern galactic dynamics. The term sounds dramatic, but the mechanism is subtle, and it depends on collective changes rather than impacts. Stars rarely collide directly, because the distances between them are enormous, and the cross-sections are tiny. The violence is in the changing field, not in collisions. Violent relaxation is the collective response to a fluctuating gravitational field, which redistributes stellar orbits toward a new equilibrium that is smoother and more mixed. A star that once followed a nearly circular path can be kicked onto a more elliptical, randomly oriented orbit, and its new energy can differ from its old one. The system's memory of the original disk can be blurred, even if individual stars remain intact and unchanged in themselves. The end state is often rounder because random motions support the structure against gravity in all directions. In images, that support looks like a spheroid, but in dynamics it is a shift from ordered rotation to dispersion. During this phase, ordered rotation can be converted into random motion, and the language of heating captures that change in plain terms. A thin disk can be heated into a thicker component, or transformed into a spheroid-dominated remnant, depending on how much angular momentum remains organised. Heating here means an increase in velocity dispersion, not a rise in temperature, and the distinction matters for understanding collisionless systems. Stars gain random kinetic energy, so their orbits become puffier and less confined to a plane. The remnant's shape reflects that change, like a shadow cast by its internal motions. The outcome depends on how much of the original angular momentum survives and where it ends up, because stars and gas do not play by the same rules. Gas can radiate energy and settle, while stars keep whatever random motions they acquire and cannot cool themselves back into a thin disk. This difference between collisional gas and collisionless stars is crucial, and it is one reason mergers can build dense centers. Gas clouds can shock, dissipate, and cool, allowing them to sink and form compact structures, while stars can only rearrange their orbits under gravity. The remnant's final appearance is therefore layered, with components that remember different parts of the encounter. This is why many major mergers produce elliptical-like remnants, even when they began as elegant spirals. The stellar component becomes dispersion-supported, while any remaining gas may form a new disk later if it retains enough angular momentum. In some cases, the remnant can be a hybrid, with a spheroidal stellar body and a regrown gaseous disk that settles over time. The timing matters because gas inflow and star formation can occur during the merger, not only after it. The remnant's final appearance is therefore a layered history, and the layers can be read with kinematics and chemistry. Yet a puzzle remains from the opening hook, and it is a puzzle that sounds almost too simple. If stars and dark matter can pass through, why do the galaxies not simply pass through forever, like ghosts crossing in the night? If the encounter were only two collisionless swarms, one might imagine endless flybys with tides raised and then forgotten. The reason they do not is that gravity creates a kind of drag, even without physical contact, and the universe provides a brake made of collective response. The answer is dynamical friction, and its intuition is as visual as it is mathematical. A massive galaxy moving through a sea of stars and dark matter gravitationally focuses material behind it, creating an overdense wake that trails along its path. That wake is not a solid object, and it is not a cloud in the usual sense because it is made of slightly rearranged orbits. It is an enhancement in density, a trailing region where particles spend more time because they were deflected and slowed. The wake's gravity then pulls backward on the moving mass, opposing its motion like a persistent hand on the shoulder. That backward pull drains orbital energy and angular momentum, and the orbit decays toward coalescence, even when nothing touches. The effect is strongest when the background is dense and the perturber is massive, because both conditions build a stronger wake. It is also stronger when the relative speed is not too high, because slower motion allows a larger wake to form and remain coherent. The process is gradual, but over cosmic time it is decisive, and it turns a flyby into a merger. Chandrasekhar formalized the idea for a massive body moving through a background of lighter particles, and his formula became a cornerstone of stellar dynamics. It links a simple concept to measurable outcomes, including how long satellites should take to sink and how quickly orbits should shrink. The intuitive picture is a boat making a wake, except the wake is gravitational, and the water is a sea of trajectories. There is no fluid, only particles responding to a passing mass, and many small deflections add up to a net drag. The mathematics captures that accumulation, turning a qualitative idea into a predictive tool. Dynamical friction is strongest for massive companions and dense backgrounds, which is why major mergers tend to complete rather than remain as repeated flybys. It is weaker for tiny satellites, which can orbit for long times before fully sinking, and some may never reach the center intact. Some satellites lose mass faster than they lose orbital energy, becoming streams before they can spiral all the way in. Others survive multiple passages, each time shedding more stars and dark matter, leaving a layered set of streams at different radii. The balance between stripping and sinking shapes the halo's architecture, and it determines whether the satellite becomes a core or a ghost. This breaking is why mergers are multi-pass events rather than single collisions, and why the sky can show multiple generations of debris at once. After the first pericenter, the galaxies swing apart, but the orbit is tighter than before, and the apocenter distance shrinks. The next approach comes sooner, and each passage repeats the pattern with new conditions, because the galaxies have already been distorted. The second act begins with altered disks, displaced gas, and a tidal field that now includes the reshaped mass distribution. The encounter is not a loop, it is a spiral. Each subsequent passage deepens the distortions, and it can rewrite features that seemed finished after the first pass. Tails can be retorqued, bridges can reform, and more mass is transferred into the halo and the intergalactic medium. A tail formed in the first pass can be bent or folded by later torques, and its stars can be spread into a wider plume. Material that was once marginally bound can be pushed over the threshold and escape, adding to diffuse intra-group light. The debris field becomes layered, with structures of different ages overlapping in projection, and the halo becomes a palimpsest. Gas adds another channel of energy loss, and it behaves differently from stars in ways that change the merger's pace. Shocks and radiative cooling dissipate orbital energy, helping the baryonic cores settle and merge faster than stars alone would predict. When gas streams collide, they can compress and heat, then radiate that heat away as infrared emission and bright spectral lines from excited atoms. Losing energy allows gas to sink deeper into the potential well, and sinking increases density, which increases cooling, which accelerates inflow. This feedback is one reason central regions can become dense during mergers, even while the outskirts are being emptied. Eventually the nuclei coalesce, and the visible fireworks of tails may fade as the debris disperses into the background. Yet the remnant's halo keeps the memory as faint streams, shells, and kinematic scars that remain in phase space. Even when the bright tidal tails disperse, the underlying correlations in energy and angular momentum can persist, and they can be detected with precise velocities. Stars that were once in a coherent tail may become a diffuse cloud, still sharing similar orbital properties like a melody spread across many instruments. With the right data, those shared motions can be detected long after the light has dimmed. All of this unfolds inside a larger, darker arena, and it is the arena that sets the rules. Dark matter halos overlap first, dominate the gravitational potential, and set the depth of the combined well long before the luminous disks truly collide. The luminous disks are embedded within these halos like lanterns inside a vast invisible fog, bright but not in control. The halos extend far beyond the visible edges, so their interaction begins early and persists late. Before the disks feel each other strongly, the halos are already exchanging energy and momentum, shaping the encounter's scaffolding. Because halos are extended, they begin exchanging energy early, and their overlap shapes the tidal field that pulls on disks long before the bright bodies touch. The halo's mass distribution sets the rotation curve, which sets how tightly stars are bound at different radii, and that binding determines how easily material can be lifted into tails. A deeper halo can hold onto outer disk stars more strongly, shortening tails, while a shallower outer potential can let them drift farther. In this way, dark matter influences the visible morphology indirectly, through the depth and shape of the potential. The tails we see are partly a portrait of what we cannot. Tidal debris and surviving satellites trace the halo's structure, and their motions can reveal what the light cannot. Stream precession, gaps, and heating can reveal subhalos, offering indirect tests of dark matter's clumpiness and the small-scale structure predicted by cosmological models. A stream is like a long, cold thermometer placed in the halo, sensitive to tiny perturbations along its length. If the halo is smooth, the stream remains thin and coherent, and its track is predictable. If it is lumpy, the stream can be perturbed, producing wiggles, density variations, or even breaks that persist as dynamical fossils. This is why mapping streams matters beyond aesthetics, and why faint outskirts are now treated as precision laboratories. The debris is a gravitational seismograph, sensitive to the mass distribution we cannot see, and it responds to forces integrated over long orbits. Each bend and broadening is a response to the cumulative pull along the path, not just a local disturbance. When astronomers model these responses, they can infer the halo's shape and the presence of unseen substructure, sometimes even constraining how concentrated the halo is. The faint outskirts thus become a laboratory for fundamental physics, where the experiment is written across the sky. In the local group, these ideas are not abstract because we live inside one of the systems being studied. The Milky Way's stellar halo is threaded with streams, and Andromeda's outskirts show shells and arcs from past accretion. Some of these structures were hinted at in early photographic plates, but they became clear only with modern surveys, careful image processing, and wide-field detectors. The halo, once imagined as smooth, is now known to be richly structured, and the structures are not rare exceptions. They are a record of many small meals, and they remind us that growth often happens quietly. Those structures imply a long history of minor mergers, and they also preview what the Milky Way and Andromeda will create in their own encounter. The local group is a quiet corner of the universe, yet it is not static, and its calm is only temporary. The galaxies are moving, and their halos already overlap in a tenuous way, like two invisible atmospheres beginning to mix. The future merger is not a sudden event, because it is the culmination of a long gravitational approach that began long before Earth formed. What will the night sky look like when the first tidal bridge begins to draw across the gap? For our future merger, models predict a first close passage in several billion years, followed by a recoil and a return. The first pass should raise dramatic tails, then the system will swing apart and the tails will stretch and thin as the galaxies separate. The exact timing depends on the transverse motion and the halo masses, which are still being refined with better astrometry and dynamical modelling. Even so, the broad narrative is robust, and it has the same beats seen in other interacting pairs. There will be a first pericenter, a separation, and then a final coalescence. The time between passages is hundreds of millions to a few billion years, depending on the orbit and halo masses, and that interval is part of the story. Dynamical friction steadily shortens the interval, tightening the dance and making each return more decisive than the last. Each passage removes more orbital energy, and each removes more angular momentum from the orbit, feeding it into internal motions and halo heating. The galaxies do not simply fall together in a straight line, because their momentum must be redistributed. They spiral inward through repeated encounters, shedding energy into their surroundings, and the surroundings remember. By the final approach, much of the outer disk material may already be displaced, and the visible disks may look frayed at the edges. The remaining cores will plunge through a rapidly changing potential, accelerating violent relaxation and mixing the stellar components more thoroughly. The remnant will likely be more spheroidal than either original disk, at least in its stellar distribution, and its rotation will be reduced or reorganized. Some gas may survive to settle into a new rotating component later, if it retains enough angular momentum and can cool. The halo will be enlarged and enriched by the debris, and its faint light will extend farther into intergalactic space. The observational challenge is that these outskirts are faint, and faintness is a technical problem as much as a conceptual one. The surface brightness of tidal streams can be far below the night sky, requiring deep optical imaging, careful subtraction, and an almost obsessive control of systematics. Scattered light, background gradients, and instrumental artifacts can masquerade as faint structures, and even the Milky Way's own cirrus can confuse the view. To see real streams, astronomers must control the entire imaging pipeline, from flat fielding to sky modelling, and then validate features across filters and instruments. The reward is not just a pretty picture, but a measurement of history. Deep surveys reveal the ghostly architecture, and they change how we interpret normal galaxies. They show that many seemingly isolated galaxies carry streams and shells, evidence that interactions are common even when no companion is obvious. In wide-field images, a galaxy can be surrounded by delicate arcs that only appear after hours of exposure, like breath on cold glass. The bright disk may look serene, while the outskirts tell a different story of past encounters and slow accretion. The message is unsettling and beautiful. What looks settled may only be well lit. Spectroscopy adds the missing dimension, because light alone can mislead when projection and background contamination are involved. Line-of-sight velocities and dispersions confirm whether a faint arc is bound debris, and they reconstruct the orbit that made it, turning a shape into a trajectory. A true stream will show coherent velocities along its length, consistent with a shared origin and a common gravitational path. A chance alignment of background galaxies will not, and its velocities will scatter. Spectra also reveal chemical fingerprints, linking debris to its progenitor, because stars carry the elemental record of the gas they formed from. Integral field data can separate overlapping components in crowded regions, where bridges, disks, and shells can lie on top of one another. It can distinguish a rotating disk from a kinematically hot shell, or a bridge from a chance alignment, by mapping velocity fields across the face. With spatially resolved spectra, astronomers can map motions like weather patterns, seeing shear, shocks, and turbulence in the gas. They can see where gas is shocked, where stars are rotating, and where random motions dominate. Kinematics turns a static image into a dynamical story, and it often reveals structure that the eye alone would miss. JWST extends the story to earlier epochs, when the universe was younger and mergers were more frequent, and it does so with both resolution and infrared vision. At high redshift, it resolves disturbed morphologies, and it sees through dust in the inner regions where optical telescopes can be blinded. The galaxies of that era often look clumpy and irregular, partly because they're gas-rich and turbulent, and partly because interactions are common. Yet within that complexity, tidal features and asymmetries still appear, and they echo the same physics seen nearby. JWST lets us connect local merger dynamics to the era of peak galaxy assembly, when the cosmic web was feeding galaxies more aggressively. In the infrared, JWST can connect outer tidal signatures to central activity, linking the faint handwriting to the bright engine. It can reveal whether a disturbed system is also building a compact dusty core, where gas is dense and heated by star formation or accretion. Dust that blocks optical light can glow in the infrared, tracing where gas is piling up and where energy is being released. By comparing outer debris with inner emission, astronomers can test whether tidal torques are driving inflow, as theory predicts. The outskirts and the nucleus become chapters of the same narrative, separated by scale but joined by gravity. Taken together, these tools turn shapes into physics, and they turn faintness into information. They let astronomers infer encounter parameters, mass ratios, and halo potentials from the debris field, and they allow competing models to be tested against real data. The practice has a history, from early photographic studies of peculiar galaxies to modern numerical simulations that reproduce tails and bridges in detail. In the 20th century, catalogues of interacting systems made the case that peculiar morphology was not rare, and early simulations showed that gravity alone could sculpt tails. As computing improved, models began to match observed systems with startling fidelity, and the debris became a quantitative constraint rather than a curiosity. The deeper lesson is that gravity is a sculptor with a long memory, and it writes in structures that outlast the drama that made them. It writes in tails and shells, then hides the script in faint light that persists after the brightest fireworks fade. A galaxy may look settled in its bright centre, yet its halo can still carry the signature of an ancient passage, preserved in geometry and motion. The question is not whether gravity leaves marks, because it always does. The question is whether we are looking deeply enough to read them, and whether we recognise our own galaxy as part of the same story. But the outskirts are only the prologue to the most consequential change. As tides torque the disks, gas is driven inward, and something ancient stirs in the centre. Next, we follow the inflow to the nucleus. The collision's quiet architect becomes a central engine, where black holes begin to matter. The outskirts were only the prologue. Tidal forces have already twisted the disks, and now the gas begins to fall. On wide shots, the system still looks like two galaxies arguing across space, their spiral arms flung outward into pale, ribbon-like tails. Yet in the inner regions, the argument has become physics. Gravity is rewriting orbits, and the cold interstellar medium is the first to yield. What looks serene at tens of kiloparsecs becomes violent within a few, because the potential changes quickly and the gas cannot pretend it is collisionless. In a merger, gravity does more than stretch tails, and it does more than shake stars loose. It breaks symmetry inside each galaxy, and that asymmetry applies torque. The effect is subtle in the beginning, an off-center mass concentration, a skewed spiral, a bar that was once weak. But the consequences compound each orbit. A perfectly symmetric disk can keep its gas circling for billions of years, because angular momentum is conserved and the forces average out. Disturb that symmetry, even slightly, and the disk develops preferred directions, overdensities that rotate, pull, and continually exchange angular momentum with the gas. In that exchange, the gas is the easier partner to move, because it can dissipate energy and settle into new paths. Bars, lopsided arms, and tidal distortions act like rotating levers, sweeping through the disk's material like a slow mechanical crank. They pull angular momentum out of gas and push it outward, often depositing it into the outer disk and tidal tails. In effect, the outskirts are paid in angular momentum, so the centre can be paid in mass. In simulations, you can watch the pattern speed of a bar sweep through the disk like a slowly turning gear, catching gas near resonances and redirecting it. Gas clouds do not follow the bar's stellar orbits exactly because gas can collide, shock and cool, so it slips, loses energy and drifts inward. The orbits become crowded, then kinked, then intersecting, and the flow begins to look less like rotation and more like traffic. The language is technical, but the picture is simple. Angular momentum is the permission slip that lets gas stay far from the centre, and torques are the hands that tear that slip in half. Once the slip is torn, the gas does not fall straight in, because it still has some rotation, but its circular path tightens into a spiral. Gas responds because it can shock and radiate, and those are the two ingredients stars largely lack. Each shock removes orbital energy, so the next orbit is smaller and faster, and the gas arrives at the centre with increasing urgency. The merger is not a single plunge. It is an angular momentum cascade step by step through nested scales. Stars, by contrast, mostly pass through one another, preserving their ordered motion even as the global potential changes. Gas is different. When streams intersect, the collisions create sharp discontinuities, and those discontinuities turn orbital motion into heat. In the densest lanes, the shocks can be strong enough to compress gas by large factors, setting the stage for molecular formation. Along bardust lanes and tidal shocks, streams converge, and the convergence is not polite. Collisions between streams convert ordered motion into heat and turbulence, and the turbulence becomes the roughness that seeds further collapse. In close-up views, you can almost read the direction of flow from the curvature of the lanes, as if the galaxy has drawn arrows in dust. Visually, those dust lanes are dark seams stitched across a bright disk, curving toward the nucleus with a sense of inevitability. They mark where gas piles up, cools, and becomes molecular, and where the flow begins to resemble a river entering a narrowing canyon. In some wavelengths, the seams vanish, but the structure remains, revealing that the darkness is not emptiness but abundance. The key change is angular momentum loss, and it is measurable in where the gas ends up. Gas that once circled at kiloparsec radii is driven into the inner few hundred parsecs, where the gravitational field steepens and the rotation curve rises. The inflow is not merely relocation, it is a change in the rules, because pressures, densities, and timescales all shift together. That distance sounds small, but it is a profound change in environment, and the numbers make it plain. The orbital time drops from hundreds of millions of years to just a few million, and the same mass now occupies a volume where gravity feels steeper and less forgiving. In the centre, a cloud does not get many chances to remain diffuse, because the dynamical clock keeps ringing. Inflow is not steady, and the merger's rhythm is written into the gas. It peaks near pericenter passages, then relaxes, then surges again as the orbit tightens and the galaxies lose energy to tides and dynamical friction. Each surge leaves behind a denser nucleus than before, like layers added to a growing core. Each close passage is like a hammer strike, but the blow lands through structure rather than impact. The disks flex, the bar-like distortions strengthen, and the gas responds with a delayed rush inward as shocks form and propagate through the rotating pattern. The delay matters, because it means the brightest starburst can occur after the most dramatic visual encounter. As gas piles up, surface density rises sharply, and the nucleus crosses thresholds that normal disks rarely approach. Freefall times shorten, and gravitational collapse becomes harder to avoid, even when turbulence tries to hold the line. The gas becomes self-gravitating on scales where it was once merely a tracer of the stellar potential. Freefall time is the clock set by gravity alone, and it is brutally simple in its scaling. When density increases by a factor of 100, that clock runs about 10 times faster, and the gas has less time to be supported by turbulence or magnetic fields. Even if the turbulence is strong, it decays and the centre does not wait. The star formation law shifts regimes, because the environment has shifted regimes first. High gas surface density produces disproportionately high star formation surface density in compact zones, and the relationship steepens as the gas becomes predominantly molecular and increasingly dense. What was once a gentle conversion becomes a rapid throughput. This is the familiar Kennicutt-Schmidt relation, but pushed into an extreme corner where the scatter has a physical meaning. In the nucleus, the gas surface density can climb by orders of magnitude, and the star formation response becomes steep, more like a runaway than a gentle scaling. The same equation is still written, but the coefficients feel different because the medium is different. In normal disks, star formation is spread out and relatively inefficient, with large reservoirs that take billions of years to convert. In merger nuclei, it becomes concentrated and unusually efficient, because the gas is forced into the dense phase that forms stars quickly. The efficiency is not magic. It is geometry and pressure, translated into collapse. A spiral like the Milky Way forms stars in scattered complexes along arms, with large regions of quiet interarm space and long-lived molecular clouds. A merger nucleus compresses the action into a region smaller than a typical spiral arm segment, and it does so under relentless tidal stress. The contrast is not only brightness but tempo. The nuclear region becomes a high-pressure laboratory, and the word pressure finally earns its weight. Molecular clouds are denser, warmer, and more turbulent than in quiescent spirals, and they are embedded in a background that is itself dense and dynamic. In such a place, even the concept of an isolated cloud becomes slippery. Pressure here is not an abstract number, and it is not a single contribution. It is the weight of gas stacked above gas, the ram pressure of converging flows, and the turbulent pressure of supersonic motions that keep clouds churning even as they collapse. Add magnetic fields and cosmic rays, and the support becomes a complicated ledger, though gravity keeps demanding payment. Cloud temperatures rise because dust and gas are bathed in intense radiation fields that would be diluted in a normal disk. Even when ultraviolet light is absorbed, the energy reappears as infrared photons that keep the environment warm and chemically active. The chemistry changes too, because warm dust surfaces and dense gas favour rapid molecule formation. Clouds collide more often in the crowded centre, and the collisions are energetic. Collisions compress gas, but also stir it, creating a fast cycling reservoir where dense clumps form, disperse, and reform. The centre becomes a place where the interstellar medium behaves less like a calm sea and more like a boiling fluid. Where the disk was once a wide plain, the nucleus becomes a traffic circle, tight and impatient. Orbits intersect, streams shear past each other, and the time between major cloud interactions can drop to a few orbital periods. The result is a constant reshuffling of density, which is exactly what gravity exploits. Dense gas fractions rise, and that rise is the precondition for a starburst's intensity. More mass sits above the threshold where gravity overwhelms turbulence, so cluster formation accelerates, and the characteristic mass of collapsing structures can increase. In other words, the environment makes it easier to build big things quickly. Observers infer this using molecular tracers that prefer dense environments, and the technique has become a cornerstone of starburst studies. Lines such as HCN brighten relative to CO, signalling that a larger fraction of the molecular reservoir has crossed into the regime where collapse is efficient and rapid. Behind the ratios is a simple statement. More of the gas is living at high density. Starbursts are not just more stars per year, and not just a brighter nucleus on a telescope image. They are a different environment, with extreme pressures and short dynamical times that change how feedback couples to gas. In a starburst, the medium is primed to respond quickly, and that quickness cuts both ways. In a calm disk, feedback has time to disperse clouds before too much gas turns into stars, because the dynamical times are longer and the gas is less compressed. In a starburst nucleus, the dynamical clock is so fast that gas can collapse and fragment repeatedly before the environment has time to relax. The burst becomes a throughput machine, processing gas into stars and back into gas again. Massive clusters form because the gas can assemble quickly, and because the background pressure helps keep it bound. The same inflow that feeds the burst also deepens the central potential, making it harder for young systems to unbind their birth material. The cluster is born in a tug-of-war where gravity often wins. The clusters are not merely large versions of open clusters, scaled up like a simple copy. They are dense, gravitationally bound systems, and their formation requires that gas reaches high density before feedback can fully unbind it. Their stellar densities can be so high that close encounters and dynamical evolution begin early, shaping their long-term survival. Young massive clusters can survive for billions of years, and their survival makes them valuable witnesses. Some may evolve into globular cluster-like systems, preserving the burst's conditions in their masses, chemical patterns, and internal dynamics. When we see old globular clusters today, we are seeing a memory that has outlived the gas that made it. This idea has a long history in extragalactic astronomy, stretching back to early studies of interacting galaxies. When observers first saw compact luminous clusters in merging systems, they recognized a possible bridge. Today's starbursts may be creating analogues of the ancient globular clusters that orbit giant galaxies. It raised an unsettling question. how much of a galaxy's older structure might have been forged in moments of chaos. The burst also imprints gradients, and gradients are the remnants' handwriting. Stars formed deepest in the nucleus tend to be younger and more metal-rich than those farther out, because the inflow concentrates both fuel and enriched material. The gradient is not always smooth, because bursts can be episodic, but the trend is persistent. Metals in astronomy are simply elements heavier than helium, and they are the ash of stellar furnaces. They build up over repeated generations of star formation, so a nucleus that continuously funnels gas inward can become chemically enriched faster than the outskirts. The enrichment is accelerated further when supernova subjecta are trapped by the deep potential and mixed back into dense gas. This is the fossil record the remnant will keep, even after the tidal tails fade into the background sky. Ages, metallicities, and kinematics will later reveal where gas concentrated and when, because stars preserve the conditions of their birth in their spectra and motions. The galaxy will look calmer, but its light will still carry the evidence. Long after the dust has settled, spectra will still carry the signatures, and the signatures can be read like a forensic report. Absorption lines will encode stellar ages, and metallicity-sensitive features will map chemical enrichment like rings in a tree, except the rings are warped by dynamics. Even the velocity dispersion can whisper where the starburst thickened the central component. Yet creation is immediately paired with disruption, because the most massive stars are impatient. The most massive stars begin reshaping the medium almost as soon as they ignite, and the starburst becomes a contest between assembly and erosion. The same density that makes star formation efficient also makes feedback interactions frequent and intense. There is almost no pause between collapse and consequence, and the timing is a crucial part of the story. The same stars that light the starburst also flood their birth clouds with radiation, and the surrounding gas must respond to that sudden energy input. In the nucleus, where distances are short, the radiation field can be overwhelming even a few parsecs away. Feedback starts with radiation, and radiation is both energy and information. Ultraviolet photons ionize surrounding gas, raising pressure and carving H2 regions into dense clouds, while also altering chemistry by dissociating molecules in exposed layers. The boundary between ionized and molecular gas becomes a moving front. Ionized gas is hotter, often near 10,000 Kelvin, and that temperature jump matters because it changes the gas's ability to resist gravity. It increases sound speed, inflates cavities, and drives expanding fronts that can erode dense structures from the inside out. In images, these regions can appear as glowing shells and filaments, tracing where photons have reached. Radiation pressure adds momentum, and momentum is what ultimately moves mass. Photons absorbed by dust push on gas, especially where the infrared optical depth is high, and photons effectively bounce multiple times before escaping. In the densest starbursts, that repeated interaction can make radiation a serious mechanical actor. In the most compact starbursts, dust becomes a crucial intermediary, and it changes what light can do. Ultraviolet photons are absorbed quickly, re-emitted in the infrared, and can scatter again, each interaction transferring momentum and helping to lift gas against gravity. The nucleus becomes a place where starlight is not just illumination, but pressure. Stellar winds arrive next, and they arrive with speed. Hot, fast outflows from massive stars inject momentum and energy, inflating bubbles inside the star-forming complex and carving low-density pockets. These winds also carry processed material, enriching their surroundings before the first supernova ever detonates. These winds are not gentle breezes, and their shock fronts can be bright in X-rays. They can reach thousands of kilometers per second, and when they collide with surrounding gas, they thermalize, creating hot plasma that expands and searches for the weaker seams. The geometry of those seams often determines whether the energy stays trapped or vents upward. Then supernovae detonate on a delay, and the delay is short enough to overlap with ongoing star formation. They heat gas to millions of Kelvin, drive shocks, and stir turbulence on many scales, from individual remnants to superbubbles. In a dense nucleus, many remnants overlap, and the collective effect becomes more important than any single explosion. The delay is short in cosmic terms, only a few million years for the most massive stars, and that timing matters. It means supernovae arrive while the starburst is still dense, still dusty, and still actively forming new stars nearby. The explosions do not end the party. They crash it while it is still in full motion. These processes combine rather than act alone, and their coupling is where regulation emerges. Radiation clears paths, winds in large cavities, and supernovae vent into the low-density channels, turning isolated bubbles into connected networks. Once the network connects to the halo, the system's behavior changes quickly. The sequence is often described as pre-processing, and it is a practical idea rather than a poetic one. Early feedback reduces the density around young clusters, so later supernovae waste less energy radiating away in dense gas, and instead push more effectively on the surrounding medium. Efficiency, here, is about where the energy goes. The interstellar medium becomes multiphase and porous, and porosity is a structural property with consequences. Cold clumps survive inside hot cavities, and interfaces radiate strongly, becoming bright in specific lines that trace mixing layers. The nucleus becomes a patchwork of temperatures and densities, stitched together by shocks. In visual terms, it is a foam, and the foam has texture. Hot gas fills bubbles and chimneys, while cold molecular knots persist like dark islands, and warm ionized filaments trace the boundaries where heat and cold meet. In time-lapse simulations, the foam appears to breathe, expanding and collapsing as feedback pulses. Feedback regulates efficiency by changing the density distribution, not merely by adding heat. It can disperse clouds, but it can also compress neighboring gas into new collapse sites, especially along swept-up shells. The same mechanism that ends one cloud can begin another. This is the paradox of feedback, and it is visible in ring-like structures around young clusters. A shock can shred a cloud, yet the same shock can pile gas into a shell that becomes gravitationally unstable, triggering a second generation of star formation along the rim. The starburst can propagate through its own debris, so the starburst can self-limit without ending, and the limiting is often rhythmic. It can flicker through cycles with gas repeatedly assembled, disrupted and reassembled, each cycle changing the local conditions. The nucleus does not choose a single state, it oscillates among them. The nucleus behaves less like a single explosion and more like a breathing engine with intake and exhaust. Gas flows in, collapses, forms stars, is partially expelled, then cools and returns, each cycle slightly altering the density field and the chemical mix. Over time, the engine can enrich itself because much of the ejector is trapped. The balance depends on depth of the potential well, and the potential is not fixed during the merger. A deeper nucleus traps more gas, so feedback must work harder to expel it, and the growing central mass can tighten the trap further. In that sense, the burst can build its own confinement. In a shallow potential, a modest push can lift gas to large heights, where it can cool and drift away. In a deep potential, the same push may only loft gas briefly, and gravity will reclaim it on a short timescale. The difference between a fountain and a wind can be the difference between temporary relief and lasting change. It also depends on gas fraction and geometry, which are set long before the first starburst ignites. Gas-rich mergers can sustain longer bursts, while gas-poor systems exhaust fuel quickly and the observational signatures diverge. In one case, the nucleus stays buried and bright. In the other, it flares and fades. Geometry matters because torques depend on how the disks are oriented, and orientation determines how strongly non-axis symmetric structures grow. A prograde encounter can amplify bars and shocks, while other orientations can distribute the response differently, still dramatic, but not always equally efficient at feeding the nucleus. The same mass can produce different outcomes because the coupling is different. In the nucleus, cooling remains fast, and this is one of the reasons starbursts can persist. Even hot gas can radiate at high density, so energy injection does not guarantee long-term heating, and the medium can return to a cold phase quickly. The center is a place where heat is produced and lost in rapid succession. Cooling is a competition between energy input and radiative loss, and the loss term is unforgiving at high density. At high density, the loss term wins easily, and hot gas can shed energy through line emission and bremsstrahlung faster than the intuition suggests. The result is that feedback often acts through momentum and structure, not simply temperature. Momentum matters more than temperature, because gravity cares about speed and mass. If feedback cannot accelerate gas above escape speed, much of it will fall back, even if it was briefly heated to extreme temperatures. The nucleus can look turbulent and violent, yet still retain most of its fuel. This is why outflows are often measured not only by temperature, but by velocity and mass loading, which tell you how much material is really moving. A hot wind that carries little mass may look impressive, yet it may not remove the cold reservoir that actually fuels star formation. The cold phase is the prize, and it is harder to steal. That fallback becomes a fountain, and fountains are a form of recycling with consequences. Gas cycles between disk and halo, mixing phases and spreading metals through repeated launches and returns, sometimes landing at new radii. Each cycle can redistribute angular momentum, subtly reshaping the remnant's future disk or bulge. In a fountain, the outflow is not a one-way door, and the return is part of the story. Gas rises, expands, cools, and rains back down, sometimes at different radii, redistributing angular momentum and leaving behind a chemically enriched wake. The halo becomes a memory buffer, holding material for later. When feedback does exceed the binding energy, outflows become winds, and winds can escape the immediate gravitational grip. They can propagate beyond the disk and into the circumgalactic medium, carrying the nucleus's imprint outward. In the most powerful cases, the wind can be seen as a bipolar structure aligned with the path of least resistance. The transition can be sudden, and it often hinges on connectivity. Once channels connect the nucleus to lower density regions above the disk, hot gas can accelerate rapidly, and the flow becomes a coherent wind rather than a stalled bubble. A porous medium is not just a consequence of feedback, it is a prerequisite for escape. Winds carry mass, momentum, and metals, and they are a transport mechanism that links a compact starburst to a galaxy-scale environment. A starburst is small on a galactic map, yet its influence can be large, because it changes what the halo contains. The halo, in turn, controls what the galaxy can become. Metals are produced inside the burst, and the burst is a factory with multiple assembly lines. Supernovae and massive star winds enrich the gas with oxygen, carbon, silicon, and iron group elements, and those elements quickly mix into the surrounding phases. Even dust grains can carry metals outward, surviving longer than the gas that hosts them. Different elements trace different sources, and the ratios can act like a clock. Oxygen and other alpha elements are made efficiently in core-collapse supernovae, while iron builds up more slowly when longer-lived stars eventually contribute. So abundance ratios can preserve a clock of star formation intensity. A fast burst leaves a different chemical signature than a slow simmer. Enrichment changes future cooling, and cooling is destiny for gas. Metal-rich gas radiates more efficiently, which can promote later condensation when the system settles and the turbulence decays. In plain terms, metals provide more ways for gas to lose energy, so the path back to cold clouds can be shorter. But enrichment also marks loss, because winds can export the very elements that make cooling easy. If the metals leave the galaxy in a wind, the remnant may lose some of its best cooling agents, and the halo may keep them instead. The galaxy's future can depend on where its heavy elements end up. This is one reason winds matter beyond spectacle, and beyond dramatic images of cones and filaments. They can regulate not just how much gas remains, but how capable that gas will be of cooling into a star-forming phase in the future. A wind is a chemical decision as much as a mechanical one. The circumgalactic medium becomes the mixing layer, and the mixing is messy. Outflows collide with halo gas, shock, cool, and seed the halo with heavy elements, while instabilities shred the boundaries into turbulent layers. The halo is not a passive container, it is an active reactor where phases exchange mass. The halo is not empty, and this realization changed modern galaxy theory. It is a diffuse atmosphere, and when a fast wind plows into it, the interaction creates shocks, instabilities, and turbulent mixing layers that spread metals far from the nucleus. Over time, the halo becomes a record of past bursts, written in ionization states. This matters for the remnant's long-term star formation, because the halo is a reservoir with a thermostat. Its metallicity and temperature shape later accretion, determining whether gas returns as cold streams, warm drizzle, or not at all. The starburst, in a sense, negotiates with its own future supply. If the halo becomes hotter and more stable, it can suppress cold inflow for a long time, and the remnant may fade into quiescence. If it becomes enriched and able to cool, it may eventually feed the remnant again, returning some of what the starburst tried to expel. The same wind can both delay and enable future star formation, depending on the balance. Observers track these winds through multiple traces, because no single wavelength tells the whole story. Absorption lines in background sources reveal cool and warm outflowing gas, while emission maps show where the gas is glowing on its own. Together they build a three-dimensional inference from two-dimensional light. When a quasar or bright galaxy lies behind the system, the wind writes its signature as narrow dips in the spectrum, and the dips become a velocity map. Those dips shift in wavelength, and the shift reveals velocity, sometimes hundreds of kilometers per second, sometimes more. The widths of the lines hint at turbulence, and the ionization states hint at temperature and radiation. X-ray emission reveals the hot phase, and it often outlines the wind's skeleton. It traces shock-heated plasma in superbubbles, chimneys, and extended halos, showing where energy is concentrated. In X-rays, the nucleus can look like a glowing ember inside a faint, expanding haze, with edges that mark shock fronts. Infrared dust emission reveals where energy is being absorbed and where it is being re-radiated. It also traces dust carried outward, sometimes far beyond the stellar disk, implying that even grains can survive a journey through harsh flows. Dust grains are tiny, but they are powerful thermometers, and they turn hidden starlight into measurable heat. The same outflow can contain all phases at once, and that multi-phase nature is one of the field's most important surprises. Cold molecular gas can be entrained in a hot wind, protected in dense clumps, and observed at high velocities despite its fragility. The presence of molecules implies shielding, rapid reformation, or both. Either way, it implies complexity. That multi-phase structure is a clue to driving, because it constrains which forces can couple to cold gas. Pure thermal pressure struggles to lift cold gas, so momentum and turbulence must contribute, and mixing layers can help transfer force. A hot wind can flow around dense clumps rather than through them, so the coupling must be engineered by the medium structure. In the most intense mergers, the starburst becomes dust enshrouded, and the story changes in visible light. Optical light fails as a census tool because dust absorbs the UV output, and the brightest activity can hide behind lanes that look like absence. The visuals change dramatically here, and the galaxy seems to dim even as it becomes more powerful. In visible light, the nucleus may look like a dim knot behind chaotic lanes of dust, while in the infrared it flares into dominance, revealing that the true power source has been hidden in plain sight. The core can look modest in visible images, and yet the bolometric luminosity emerges in the infrared as reprocessed starlight. The galaxy becomes a lesson in how perception depends on wavelength. Bolometric luminosity is the total energy output across all wavelengths, and it is the honest accounting. In buried starbursts, much of that total is not lost. It is simply shifted, converted into infrared photons that escape where ultraviolet light cannot. The dust is not merely obscuration, it is a reprocessing engine. This is the buried phase of luminous infrared galaxies, and it has a specific historical weight. Star formation rates can be extreme, yet the primary emission is warm dust continuum, and early infrared surveys forced astronomers to accept that the universe could hide its brightest growth behind dust. The discovery reframed cosmic star formation history, because distant dusty systems could dominate the budget. JWST changes what can be measured in that phase, and it changes it by resolving the hidden structure. Near and mid-infrared imaging penetrates dust and resolves compact star-forming structures, separating what once blurred into a single core. Where earlier telescopes saw a single glowing nucleus, JWST can reveal substructure, knots, arcs, and embedded clusters. Those knots can be separated by only tens of parsecs, and yet they can differ in age and obscuration. Some are still wrapped in their natal cocoons, glowing through warm dust, while others have begun to clear cavities and show sharper line emission. The nucleus becomes a map of evolutionary stages packed into a tiny area. Spectroscopy adds diagnostics, and diagnostics turn images into physical conditions. PAH features trace photodissociation regions, while fine structure lines trace ionized gas and radiation hardness, allowing a census of how harsh the environment truly is. The spectrum becomes a fingerprint, and each feature is a ridge in that print. PADs, or polycyclic aromatic hydrocarbons, are complex molecules that fluoresce under ultraviolet light, and they live at the edge of destruction. Their presence and strength help locate the boundary zones where molecular gas is being irradiated, but not fully destroyed. When PADs weaken, it can signal either extreme radiation or a change in dust processing. Fine structure lines from ions such as neon and sulfur respond to the energy of the radiation field, and they respond differently depending on ionization potential. They let observers infer whether the power source is dominated by young stars and how intense the ionization is inside the dust-shrouded core. In a buried nucleus, Such lines can be among the few direct clues to what is happening. Warm dust continua measure embedded power, and line ratios help separate starburst heating from harder sources, even when both are obscured. This separation is subtle, and it is one reason infrared spectroscopy is so valuable. Because dust hides the direct light but cannot erase the imprint of the radiation field on surrounding gas, the gas still remembers what illuminated it. GEFST also measures kinematics in key lines, and kinematics reveal the struggle in motion. Velocity shifts and broadened profiles reveal inflow, turbulence, and outflow in the same nucleus, sometimes within the same beam. A broadened line can mean many things: multiple components, strong turbulence, or fast winds, and spatial mapping helps untangle them. By mapping those profiles across the nucleus, observers can reconstruct how gas is moving and where the flow is being accelerated or stalled. These measurements connect mechanics to outcome, because they test whether torques deliver gas faster than feedback can remove it. They also reveal timing, because the spectral signatures evolve as clusters age and supernovae begin to dominate. Very young regions show strong recombination lines and signatures of massive stars still embedded in dust, with line profiles shaped by dense environments. Slightly older regions show evidence of mechanical energy injection, shocked gas, expanding shells, and altered line ratios that betray a harsher medium. The nucleus is a mosaic of ages, and the mosaic is readable. The central question returns with higher stakes because the merger has concentrated the decision into a small volume. In a collision, gas is the component that can change state, change phase, and change fate, and that flexibility makes it powerful. Stars mostly remember their initial conditions, preserving orbital histories in their motions, while gas negotiates with every force it meets. Now we ask what the fate can be, and we keep the options on the table. Does the burst consume the gas, expel it, or recycle it into another round of star formation? The answer is not universal, and that uncertainty is part of the mystery, because small differences in geometry and timing can tip the balance. Two mergers can look similar from afar, yet differ in gas fraction, orientation, and central depth, and those differences can steer the outcome toward very different futures. Triggering is the easy part because torques and shocks can ignite a burst quickly once enough gas reaches high density. A small change in density can produce a large change in star formation rate, because collapse accelerates rapidly once the gas crosses critical thresholds. In that sense, the merger does not need to invent new physics, it only needs to push ordinary gas into extraordinary conditions. Quenching is the harder outcome to explain, because it requires that star formation becomes difficult even if some gas remains. Quenching is not simply the absence of fuel, but a change in the system's ability to turn available gas into dense, collapsing clouds. One route is consumption, and it is the simplest to imagine. If the burst converts most dense gas into stars rapidly, the remaining gas may be too diffuse to collapse, at least for a time. In this case, the starburst behaves like a fast burn in a furnace, leaving behind a lower density medium that can orbit without fragmenting. Another route is expulsion, and it is the most visually dramatic. If winds remove a large fraction of the cold reservoir, the nucleus can be starved on short timescales, and the star formation rate can drop quickly. Outflow cones, high-velocity absorption, and extended X-ray halos can all indicate that the system has begun exporting the very material it would otherwise use. A third route is heating and pressurization, and it can operate even without full escape. Hot gas and turbulence can keep remaining gas from settling into gravitationally unstable clouds, raising the effective sound speed and thickening the gas layer. Turbulence acts like an added pressure term, and it can raise the threshold for collapse so that gas remains marginally stable. Stabilization can also come from structural change, and this is where dynamics becomes destiny. Bulge growth raises central shear and epicyclic frequency, making disks harder to fragment, because differential rotation can tear overdensities apart before they collapse. This is a dynamical form of quenching, and it can be subtle, because the gas is still present but its instabilities are suppressed. So the merger can build the very structure that suppresses later star formation, and the remnant's appearance follows. The remnant becomes more spheroidal and less prone to new spirals, because the disk component is heated and the central mass concentration grows. The visual transformation is striking, as spiral patterns fade and the light distribution becomes smoother. The galaxy begins to resemble an elliptical or a bulge-dominated system, even though the memory of the merger remains in shells, streams, and kinematic scars. Yet quenching is rarely final in one step, because gas can fall back, cool, and reignite star formation if the halo remains able to supply fuel. A quenched remnant can still be a temporary state, a pause rather than an ending. If the halo cools efficiently, or if later accretion resumes, the system may rebuild a disk, or at least form a new, smaller generation of stars in the central regions. The outcome depends on whether the halo stays hot, because a hot, stable halo can prevent cold accretion and prolong quenching after the burst. This is one reason massive galaxies are more easily quenched, because their halos can support long-lived hot atmospheres. This is where another actor becomes relevant, and the narration begins to lean toward the next chapter. A compact engine can add energy and momentum far beyond what stars alone can provide, and the merger is already delivering fuel to the right address. We can see the setup in the inflow itself, because gas is being delivered to the inner tens of parsecs, where gravity becomes extremely steep. At these scales, the story becomes more intimate, and the cascade continues. The gas is no longer responding only to global bars and tidal distortions, but to nested structures and local instabilities that can continue the angular momentum cascade toward the very center. The starburst competes for that fuel, because dense clouds form stars, but some gas keeps losing angular momentum and moves even deeper. This competition is visible in the bookkeeping of mass, and the ledger has multiple columns. Some fraction is locked into stars and clusters, some is driven outward in winds, and some continues inward, slipping through the star-forming ring and approaching the central engine's domain. The nucleus becomes a layered system, clusters and clouds embedded in dust, winds carving channels upward, and a deeper inflow threading through the chaos. At the very center, the potential is dominated by a supermassive black hole, and its influence is small in size but large in consequence. Its sphere of influence is small, but its efficiency is enormous, because accretion converts gravitational energy into radiation and mechanical output with remarkable effectiveness. A black hole does not need much mass to matter, and that is what makes it dangerous to ignore. If gas reaches the innermost region and accretes, the conversion of gravitational energy into radiation and mechanical output can outshine the entire starburst, even when the accreted mass is modest. The merger therefore builds tension in two directions, because it creates stars at high speed, and it also stockpiles fuel for something more compact. The question is whether the inward stream can remain coherent long enough to feed the central object. Even before an active nucleus turns on, the conditions are being prepared, and the preparation is visible in dust and density. High density, high obscuration, and strong inflow are the prerequisites, and the merger supplies all three. In other words, the merger is already building the stage, assembling the fuel, thickening the curtain of dust and compressing the environment until a small region can dominate the fate of the entire remnant. The fossil record will remember both sides of the struggle, and it will remember them for different reasons. Cluster populations, metallicity patterns, and outflow-enriched halos will persist, long after the luminous burst has faded. Clusters preserve the intensity of the burst, because their masses and ages reveal how quickly gas was converted into stars, while metallicity gradients preserve the direction of flow. Enriched gas tends to collect where the inflow is strongest, and the stars formed there inherit that enrichment. In the local group future, the same physics will apply, and the thought is both distant and familiar. If enough cold gas remains, Milky Way and Andromeda could experience a central burst, driven by torques and shocks that funnel gas inward. The details would differ, because the gas content will evolve between now and then, and prior star formation will change the metallicity and structure of both disks. Still, the core mechanism, torques driving inflow, density rising, and feedback responding, would be familiar. If less gas remains, the burst may be weaker, but inflow and feedback will still reshape what is left, and the center will still be the battlefield. Even a modest burst can reorganize the central 100 parsecs, and the reorganization can last. It can build clusters, thicken the dust layer, and launch fountains that redistribute metals, leaving a remnant whose central chemistry and kinematics carry the imprint of a brief, intense episode. Either way, the collision is slow alchemy because gravity concentrates gas, stars ignite, and feedback tries to blow the furnace apart. The alchemy is slow only on the outside, where the tidal tails drift and the galaxies take hundreds of millions of years to fully settle. In the nucleus, timescales are short, and the system can change character within a few million years. an instant compared with the age of the galaxies that began the encounter. The heart of the storm is not calm, and it never truly rests. It is a compact region where creation and destruction are simultaneous, and where the next chapter is waiting. In the visuals, the centre is a bright, obscured knot, surrounded by streaming dust lanes, like veins feeding a hidden organ. Every wavelength tells a different truth, and together they reveal a place where gravity and light are locked in constant negotiation. The centre becomes a furnace, yet something even more compact sits at the core waiting for fuel. Next, we follow the inflow past the Starburst. We enter the realm of black holes and active galactic nuclei. The centre became a furnace in the last chapter, but the deepest engine stayed hidden. Beneath the glare of newborn stars, a darker power sits in most massive galaxies, an object defined less by what it emits than by what it forbids. A supermassive black hole does not shine by itself, yet it sculpts the motions of everything near it, quietly enforcing gravity's rules. In a sense, it is the purest kind of presence, mass concentrated so extremely that space and time bend around it. The event horizon is not a surface you could land on, but a boundary in space-time. Cross it, and even light cannot return. Outside that boundary, however, the black hole's influence is ordinary gravity, and that is why it can hide in plain sight. For more than a century, astronomers suspected such compact masses from stellar speeds, although the idea sounded almost mythic at first. Early hints came from the way stars moved in dense clusters and galactic centres, where the implied mass-to-light ratios became uncomfortably large. Only in the late 20th century did the evidence harden, as spectroscopy and sharp imaging revealed stars whipping around invisible centres. In our own Milky Way, the orbits near Sagres became a kind of celestial courtroom, precision measurements turning an inference into a near certainty. Year after year, individual stars traced tight ellipses, accelerating near pericenter as if slung by a hidden weight. The mass had to be millions of suns packed into a region smaller than our solar system, leaving few alternatives besides a black hole. That confirmation did more than settle a debate because it reframed what a galaxy's centre really means. The nucleus is not merely where starlight peaks, but where gravity's bookkeeping is most strict and most consequential. When galaxies collide, it is this bookkeeping, slow, relentless, and cumulative, that brings the giants together. In a major merger, two such engines are dragged toward one another, not by impact, but by gravity's slow accounting. The black holes do not collide like billiard balls, because space is mostly empty and their cross-sections are tiny. Instead, the galaxy's mass distributions overlap, and the merger's changing gravitational potential does the work over hundreds of millions of years. At first, the black holes are simply passengers inside their own galaxy's nuclei, embedded in dense stellar cusps and gas-rich central disks. Each nucleus is wrapped in stars, gas and dark matter that still remembers its original centre, like two knots of identity inside a single disturbed body. On wide scales, the merger looks messy and luminous, yet the black holes remain ordinary components of their respective cores. As dynamical friction drains orbital energy, the nuclei sink through the combined potential, and the separation shrinks from tens of kiloparsecs to a few. Dynamical friction is not a literal friction, but a gravitational wake, an overdensity of stars and dark matter trailing the moving nucleus. That wake tugs backward, converting ordered orbital motion into heat-like random motions in the surrounding population. The effect is subtle in a single moment, but decisive across time, because every orbit leaves a faint imprint in the background. Stars behind the moving nucleus are slightly focused, like iron filings aligning around a magnet, and the resulting asymmetry steals momentum. In simulations, you can watch the orbit decay as if the galaxy were moving through invisible molasses, except the molasses is gravity itself. Visually, this early phase can resemble a double heart, two bright centres inside one warped system. Long tidal tails arc outward, and dust lanes cut across the starlight like charcoal strokes on a glowing canvas. In deep images, the outer halos overlap first, while the inner bulges remain distinct, two cores circling inside a shared envelope. Sometimes both black holes accrete at once, and we call it a dual AGN. In that case, the merger briefly hosts two compact engines, each lighting its own immediate environment with hard radiation. Sometimes only one is obvious, while the other is active but buried, or starved, or simply too faint against the starburst's glare. The rarity of clear dual AGN is not only about astrophysics, but also about selection, because the universe does not label its engines for us. Two nuclei can be separated by a kiloparsec and still blur into one source at typical survey resolution. Even when we resolve them, their brightness can fluctuate, and a snapshot can catch one engine between feeding episodes. The mystery is not whether black holes exist in mergers, but whether we can see them when they matter most. The same inflow that feeds them also builds a curtain, because gas and dust pile into the inner hundreds of parsecs. Optical light can be absorbed and scattered until the nucleus looks quiet, even while it is growing behind the veil. Dust is efficient at hiding the truth because it is made of grains comparable in size to optical wavelengths. Those grains absorb ultraviolet and visible photons, then re-radiate the energy as infrared heat. An honest signature, but one that looks very different from a classic optical quasar. In a merger, where gas is compressed and stirred, the dust column can become thick enough to erase the usual clues. This is why optical surveys miss many growing black holes, especially in dusty mergers. The classic signatures like bright broad lines and blue continua can vanish behind extinction. A merger can hide its most energetic phase in plain sight, turning the brightest engine into a darkened room. There is a second complication that makes the nucleus even harder to read. Starburst can mimic parts of an AGN spectrum because massive stars produce intense ultraviolet light and strong emission lines. When the central kiloparsec is forming stars at a furious rate, the galaxy can look active without revealing which engine is responsible. In a crowded nucleus, light from many sources overlaps, and the spectrum becomes a blended testimony. Hot young stars ionize gas and create nebular lines, while supernova shocks add additional excitation and turbulence. The result can resemble an AGN in broad strokes, even if the black hole is quiet, or it can conceal an AGN that is truly there. Infrared and X-ray observations reopen the door because they penetrate where optical photons fail. Hot dust heated by an AGN glows strongly in the mid-infrared, often with a smooth continuum that rises like a warm ember. Hard X-rays can pass through large columns of gas, revealing accretion even when the nucleus is heavily obscured. In the infrared, the physics is simple in concept, even if complex in detail. Dust grains near an AGN can reach hundreds of Kelvin, radiating strongly at wavelengths of a few to a few tens of microns. Star-forming regions also heat dust, but typically to cooler temperatures, producing spectral features and slopes that can be distinguished with careful measurements. Those differences can be subtle, because starbursts also create warm dust, especially in compact regions, yet AGN-heated dust often produces a smoother, more power law-like continuum, while star formation leaves stronger aromatic features and a different temperature mix. In practice, astronomers fit templates and models, looking for the telltale excess that points to a buried engine. X-rays tell a complementary story because they originate close to the black hole itself. The inner accretion flow produces a hot corona of energetic electrons that upscatter lower energy photons into the X-ray band. When we detect hard X-rays, we're often seeing a direct trace of the engine's immediate neighbourhood. Yet even X-rays have limits, because the densest obscurers become Compton thick. In that regime, photons scatter repeatedly, losing direction and sometimes energy, and the direct view is suppressed. We infer the engine through reflected components, iron lines, and the surrounding dust's reprocessed heat, and uncertainty becomes part of the measurement. A Compton-thick nucleus can behave like a lighthouse wrapped in fog. The beam exists, but most of what reaches us is indirect, light bounced off surrounding material or re-emitted after being absorbed. The iron K-alpha line near 6.4 keV becomes especially valuable here, because it can stand out as a fluorescent echo of hidden X-ray illumination. JWST adds a new set of diagnostics in the infrared, where buried nuclei can be separated from starbursts more cleanly. Its sensitivity allows us to detect faint continua and subtle spectral shapes that older telescopes could not isolate. AGN-heated dust produces characteristic colours and spectral slopes, distinct from cooler star-forming dust. JWST's spectrographs also let us examine emission lines in the near-infrared, where extinction is lower than in the optical. Near-infrared emission line ratios can reveal hard ionizing fields, even when the optical lines are erased. Lines from highly ionized species can act like fingerprints of an AGN, because star formation rarely produces the same extreme radiation field. In visuals, This is where the merger nucleus transforms from a smudge into a landscape. A dusty central region that looked opaque in optical light becomes layered in the infrared. Filaments, knots, and bright compact sources emerging like islands through fog. The camera seems to peel back the dust, not by removing it, but by choosing wavelengths the dust cannot easily block. This capability matters because mergers are not uniform, even within a single nucleus. The gas can be clumpy, filamentary, and turbulent, with dense knots embedded in more diffuse flows. A black hole's fuel supply can therefore be intermittent, brief surges followed by lulls, so the observable signatures can flicker in both time and wavelength. JWST can also resolve compact structures in merging cores, where older telescopes blended everything together. A single luminous nucleus can break into multiple components, each with different obscuration and excitation. In images, what looked like one bright knot can become a crowded scene of star clusters, dust-enshrouded regions, and a compact central source. That improved resolution changes interpretation as much as it changes aesthetics. If the infrared light is spread over many star-forming clumps, the AGN may be weaker than assumed. If a compact point source dominates at certain wavelengths, the black hole may be the true driver, merely disguised by dust geometry. To understand why mergers awaken black holes, we need a simple picture of accretion that stays faithful to the physics. Gas that reaches the black hole cannot fall straight in, because it carries angular momentum from the galaxy's rotation and turbulence. It forms an accretion disk, where friction and turbulence convert orbital energy into heat, and heat becomes radiation. In practice, the friction is often magnetic and turbulent rather than collisional. The magnetorotational instability can tangle magnetic fields and drive angular momentum outward, allowing mass to spiral inward. The result is a disk that behaves like a cosmic conveyor belt. Matter moves in, energy moves out. As the gas compresses and heats, it radiates across the spectrum, and the color of that radiation encodes temperature. The outer disk can glow in optical and ultraviolet, while the hottest inner regions push toward extreme ultraviolet that we rarely see directly. Above the disk, the corona adds X-rays, turning the engine into a multi-wavelength beacon. The efficiency is startling, because gravity near a black hole is deep and steep. A small amount of mass can release an enormous amount of energy as it spirals inward, far more than nuclear fusion can extract from the same mass. That is why an AGN can rival or exceed the luminosity of an entire galaxy, even though the engine is smaller than a solar system. The disk's inner edge sits close to the event horizon, and that distance depends on the black hole's spin. A rapidly spinning black hole allows stable orbits closer in, increasing the potential energy available for radiation. In a merger, spin can be altered by accretion and by the eventual black hole coalescence, adding another layer to the story. There is also a limit that keeps the growth from becoming arbitrarily fast. As radiation pushes outward on electrons and dust, it can balance gravity's pull inward. This balance defines the Eddington limit, a rough ceiling on steady accretion for a given black hole mass. The Eddington limit is not a hard wall, but it is a useful scale for the story. Real accretion can exceed it briefly, especially if the flow is geometrically thick and radiation escapes unevenly. Still, if accretion approaches that rate, the nucleus brightens dramatically, and the surrounding gas feels strong radiation pressure. In a merger, inflows can raise accretion rates toward this regime, at least in bursts. The same tidal forces that compress gas into star-forming clouds can also funnel it inward, feeding the central parsecs. The nucleus may cycle between obscured growth and more exposed brilliance, depending on how the gas rearranges itself. Merger-driven inflows are the bridge between galaxy-scale tides and black hole-scale disks. Torques from bars, asymmetries, and tidal distortions remove angular momentum from gas, letting it sink inward rather than orbiting safely at large radii. Shocks and radiative cooling let the gas settle deeper, and nested instabilities can carry it from kiloparsecs to parsecs. The visual counterpart is often dramatic. Dust lanes become sharply defined, curving into the centre like dark rivers, while bright star clusters ignite along compressed ridges. In some systems, you can almost trace the path of inflow by following the dust's geometry, spirals tightening as they approach the hidden core. The last step is the hardest to observe, because it happens behind dust and inside extreme physics. We infer it through variability, compact infrared emission, and broadened lines that suggest fast motions. The centre becomes a place where evidence is indirect, and where models must stand in for images. Variability is especially revealing because it encodes size. If a source brightens and dims over days or weeks, the emitting region cannot be larger than light can cross in that time. In that way, time becomes a ruler, letting us estimate scales that no telescope can resolve directly. When both galaxies bring gas, the merger can create a short-lived phase of extraordinary luminosity. Some of the brightest objects in the universe, including luminous quasars, appear linked to mergers, especially at epochs when galaxies were more gas-rich. The idea is not that every merger makes a quasar, but that the right merger can. Historically, the connection between quasars and galaxies was itself a revelation. Quasars were first identified as star-like radio sources with enormous redshifts, implying vast distances and impossible luminosities. Only later did the picture settle into a central engine model, where accretion onto a supermassive black hole provides the power. That historical arc matters, because it mirrors how evidence accumulates in astronomy. First, a mystery, then a set of constraints, then a physical model that survives better data. The quasi-stellar name itself is a fossil from that era, a reminder that even the brightest engines once masqueraded as points of light. What other engines are masquerading now, hidden by dust and distance? A quasar phase requires fuel delivered quickly and in large quantity, and a black hole ready to accept it. The merger provides the delivery system by destabilizing gas and compressing it inward. The black hole provides the conversion, turning infall into light with an efficiency stars cannot match. But light is not the only output, and this is where the story's stakes rise. An AGN can push back on its own fuel supply through feedback, turning growth into a self-limiting process. The same accretion that makes the nucleus bright also makes it capable of reshaping the remnant. Feedback comes in several channels that operate at different scales. Radiation pressure can drive dusty gas outward, especially when the nucleus is deeply embedded and photons are trapped long enough to share their momentum. Fast winds can be launched from the inner disk, carrying momentum and energy into the surrounding interstellar medium. These winds can reach thousands of kilometers per second, and they can carry signatures of ionized atomic and even molecular gas. The wind's origin may lie in the disk's atmosphere, where magnetic fields and radiation combine to accelerate material. Once launched, the flow can shock against ambient gas, converting kinetic energy into heat and turbulence. Jets add another mode, narrow and relativistic, capable of drilling through dense gas. They can inflate bubbles in hot halos and deposit energy far from the center, sometimes lighting up radio lobes that extend well beyond the visible galaxy. Not every AGN makes powerful jets, but when jets appear, they can dominate the mechanical impact. The difference between wind-driven and jet-driven feedback is partly a matter of geometry. Winds are often wide-angle, sweeping through a large solid angle, while jets are needle-like and directional. In a merger, where the gas distribution is irregular, that geometry can decide whether feedback clears the nucleus or merely punches escape tunnels. These mechanisms can heat gas, expel it, or keep it turbulent enough to resist collapse. In that way, AGN feedback can quench star formation, even if some gas remains bound to the remnant. It can also regulate black hole growth, because pushing gas away reduces the accretion supply. The outcome is not universal, and that uncertainty is part of the merger's mystery. In some systems, feedback seems to clear the nucleus and shut down star formation quickly, leaving a post-starburst signature in the stellar population. In others, star formation and AGN activity coexist, implying that feedback couples imperfectly to the cold gas. We can frame the problem as a competition of timescales and geometries. If inflow delivers gas faster than feedback removes it, the nucleus stays active and buried, and the galaxy can glow in infrared while looking optically calm. If feedback opens channels and accelerates gas above escape speed, the remnant can be left gas-poor and fading. Observations show outflows with velocities of hundreds to thousands of kilometers per second. Some carry molecular gas, which is surprising because molecules are fragile in harsh radiation fields and can be dissociated by ultraviolet photons. Their presence implies shielding, rapid reformation, or entrainment in dense clumps, and each option points to complex structure. Molecular outflows also raise a pointed question about efficiency. If cold gas is removed, star formation can be suppressed quickly because the raw material is physically displaced. If the outflow is mostly hot or ionized, the cold reservoir might survive, and quenching could be slower or incomplete. In mergers, the Starburst and the AGN can drive winds together, and separating them is difficult. Supernovae and stellar winds inject energy on large scales, while the AGN injects energy from the centre outward, and the two can overlap in both space and time. Line ratios, spatial structure, and multi-wavelength data help, but degeneracies remain. The nucleus is a layered engine, and our measurements often mix its layers. A single spectrum can include emission from star-forming regions, shocked gas, and the AGN's narrow line region, each responding to different physical drivers. The challenge is not only detection but attribution, deciding which process dominates the observed signal. As the galaxies continue to merge, the black hole's own journey becomes a dynamical story. Once the stellar nuclei approach closely, each black hole sinks through the dense central region by dynamical friction, now acting against a background of stars that has been stirred and reshaped. The separation can fall to tens of parsecs, then to a few. At these scales, the two black holes become a bound binary rather than two independent wanderers. Their mutual gravity dominates their relative motion, and the surrounding stars respond to the binary as a single, time-varying potential. The binary's orbit contains energy that must be removed for coalescence to occur. The question becomes how the system continues to shrink when dynamical friction alone becomes inefficient. Early on, each black hole drags a wake through a large background, and the drag is strong. Later, when the binary is tight, the background cannot easily form the same wake, and the easy braking fades. This is the beginning of the so-called final parsec problem. The phrase is memorable because it points to a bottleneck at roughly parsec scales, where simple mechanisms may stall. Whether nature truly stalls there depends on details of the remnant's shape, its gas content, and the availability of stars on the right orbits. From here, the binary must harden through interactions with stars and gas. Stars that pass close can extract energy through three-body encounters, being flung outward while the binary tightens. The ejected stars can carve a lower density core in the remnant, leaving an imprint that may persist long after the merger looks settled. This requires a steady supply of stars on lost cone orbits that reach the binary. The lost cone is a region of phase space, not physical space, an inventory of trajectories that bring stars close enough for strong interaction. If those orbits are used up faster than they are replenished, the binary's hardening rate can slow. The lost cone can be depleted, leaving the binary stalled if the stellar distribution is too smooth. Triaxial shapes, chaotic orbits, and continued perturbations can refill it, keeping hardening active. Real merger remnants are not perfect spheres, and that asymmetry may be the escape route. Gas can also help if a circumbinary disk forms and exchanges angular momentum with the pair. Torques in the disk can drive inflow while shrinking the orbit, though the details depend on disk thickness, viscosity, and fragmentation into stars. In gas-rich mergers, this pathway may be common, but it remains hard to confirm directly. A circumbinary disk is not a quiet structure. The binary can open a central cavity, forcing gas to stream inward in narrow, time-dependent flows. Those streams can modulate accretion, potentially imprinting periodic signals, although real systems add noise through turbulence and changing obscuration. We infer these stages through indirect signatures, like dual nuclei at kiloparsec scales, and periodic variability hints at smaller separations. Some systems show double-peaked narrow lines, though those can also arise from outflows and rotating disks. The evidence is suggestive, but rarely decisive. There is a reason the evidence is so slippery. The spatial scales shrink faster than our ability to resolve them, and the timescales lengthen beyond a human lifetime. We are forced to reconstruct a sequence from snapshots of many galaxies, each caught at a different moment and each complicated by its own geometry. Eventually, if the separation becomes small enough, gravitational waves take over. At that point, the binary loses energy primarily by rippling spacetime itself, a prediction that emerged from general relativity and took a century to confirm directly in other mass regimes. The final inspiral accelerates, and the merger becomes inevitable, even if the surrounding gas is chaotic. For supermassive black holes, these gravitational waves are low frequency, far below the band of ground-based detectors. We cannot hear them with LIGO because the periods are months to years rather than fractions of a second. We need different instruments, and the universe forces patience again. Pulsar timing arrays offer one path, using millisecond pulsars as a galactic scale clock network. A passing gravitational wave slightly shifts pulse arrival times, creating correlated patterns across the sky that cannot be explained by individual pulse and noise alone. The signal is subtle, but it accumulates, and recent results suggest a background consistent with many distant binaries. That background is like a cosmic murmur, the combined effect of countless supermassive binaries evolving across the universe. It does not identify a single merger in most cases, but it tells us the population exists and is active. It also hints at how often galaxies merge and how efficiently binaries reach the gravitational wave regime. Future space-based detectors like LISA aim to detect individual supermassive black hole mergers more directly. In its band, inspirals can be tracked over long durations, turning the invisible finale into a measurable waveform. That waveform encodes masses, spins, and orbital evolution, revealing the hidden core of the merger story. Even then, much remains concealed, because gravitational waves tell us about the binary, not the surrounding gas. The electromagnetic counterpart could be bright, faint, or absent, depending on how much material remains near the pair and how it is arranged. We may detect the space-time event without seeing the light, and that mismatch will be part of the new era. If light does appear, it may arrive in complicated ways. Gas near the binary can be shocked, heated, and rearranged during the final stages, potentially producing flares or changing spectral signatures. Yet the same dust that hides the growth can also hide the finale, leaving only a gravitational imprint. After coalescence, the remnant black hole may not sit still. Gravitational waves can carry momentum asymmetrically, delivering a recoil kick that depends on mass ratio and spin orientation. The merged black hole can be displaced from the center, oscillating through the remnant or, in extreme cases, escaping entirely. A recoiling black hole would leave observable relics if it carries an accretion disk or continues to accrete from ambient gas. It could appear as an offset AGN, spatially displaced from the stellar nucleus by hundreds or thousands of light years. It could also show velocity offsets in broad emission lines, hinting that the engine is moving relative to the host. Searching for these relics is difficult because other processes can mimic offsets. Dual AGN, disturbed gas kinematics, and outflows can all shift-line centroids, and mergers are full of disturbed kinematics. Confirming a recoil requires consistent spatial and spectral evidence, and the best candidates remain debated. The merger can also leave disturbed nuclear gas, warped disks, and long-lived post-merger AGN phases. Even after the galaxies look settled, the central region can remain out of equilibrium, with misaligned angular momentum and lingering turbulence. Gas can continue to trickle inward, reigniting activity long after the tidal tails have faded. This lingering activity complicates the narrative of cause and effect. Did the AGN quench star formation, or did star formation simply consume the gas first, leaving the AGN to fade later? In real remnants, both can happen, and the sequence may differ from one merger to the next. This is why black holes matter for the fate of the whole remnant, not just for a dramatic finale. If AGN feedback heats or expels gas, it can reduce the remnant's final stellar mass by shutting down star formation. It can also help establish the tight correlations we observe between black hole mass and bulge properties, though the causal direction is still argued. Those correlations, often summarized as relationships between black hole mass and stellar velocity dispersion, or bulge mass, are among the strongest hints of coevolution. They suggest that galaxies and their central engines do not grow independently, even if the coupling mechanism varies. In mergers, the coupling is tested under extreme conditions, when inflow and feedback are both amplified. The correlations suggest coevolution, but the mechanism remains partly hidden. Feedback is a plausible regulator, yet inflow physics and star formation also shape bulges, and they can do so without any direct intervention from the black hole. In mergers, all these processes happen together, making it hard to isolate cause from coincidence. We return to the local group because our future collision will also bring two black holes into the same nucleus. The Milky Way's S-Ray is modest by quasar standards, while Andromeda's black hole is larger and sits in a more massive bulge. Their eventual pairing depends on how much gas remains and how the stellar cores evolve during the merger. The visual is almost unsettling in its familiarity. The night sky would change slowly at first, with Andromeda swelling over millennia, then stretching into arcs as tidal forces pull stars into long streams. Somewhere inside that evolving glow, two central dark masses would begin the same quiet descent we see in distant mergers. The timeline is long, and the uncertainties are real. Improved astrometry refines Andromeda's transverse motion, and better halo mass estimates refine the merger schedule, because the dark matter halos set the gravitational stage. But the broad arc remains, and it ends with a binary that must harden, then radiate gravitational waves, then become one. Whether the event is luminous or buried depends on conditions we cannot predict with certainty. The gas content of both galaxies will change over billions of years, and future star formation will alter their central structure and dust supply. The merger's black hole chapter is therefore partly forecast and partly mystery. Still, we can say what the physics demands. Two massive galaxies rarely merge without bringing their central black holes into the same gravitational well, because the black holes ride inside the densest parts of their hosts. The nuclei sink, the pair forms, the orbit tightens through stars and gas, and space-time eventually carries away the last energy. The deepest irony is that the most decisive moment may be the least visible. Dust can hide the feeding, and extreme gravity hides the final orbit, so the climax can occur behind multiple curtains. We infer the giants by their effects, by their heat in the infrared, by their hard photons in X-rays, and by the subtle timing of pulsars, and then the story turns outward again, because the nucleus does not keep its secrets to itself. If black holes and feedback can shut down star formation, they can change what the merged galaxy becomes, altering its colour, its structure, and its future ability to make new stars. We leave the central parsecs and ask what form the remnant takes once the engines have spoken. We move outward from the hidden core to the galaxy-scale aftermath. The collision has rewritten the centre, and now we measure the new whole. And then the story turns outward again, because the nucleus does not keep its secrets to itself. A merger is not finished when the starburst fades, or the AGN quiets, because the brightest fireworks are only the middle act. When the dust settles, the final question is structural. What kind of galaxy remains after gravity has resorted everything it was given? The answer is written in shape, in motion, and in the quiet distribution of mass that no telescope sees directly. Even the word remnant can mislead, because it suggests leftovers rather than a new equilibrium assembled from disrupted parts. Two spirals can meet as ordered disks and separate to something smoother and rounder, like a familiar face blurred into a new silhouette. The remnant can look elliptical-like, with a soft glow and no obvious arms, or it can rebuild a disk and pretend the collision was only a detour. In deep images, the pretense often fails. Faint shells, ripples, and tidal arcs linger like fingerprints in low surface brightness light. These features are not decoration, they are dynamical afterimages, and they fade only as orbital phases mix, and the debris dissolves into the background. The difference begins with a simple fork in the road, although the road itself is carved by invisible mass. Some encounters are major mergers, where masses are comparable and the violence is global. Others are minor mergers, where a small companion is swallowed and the primary survives. That distinction sounds tidy, but nature blurs it with geometry, gas content, and timing. Details that decide whether a disk is erased or merely bruised. Even the internal structure matters, because a dense bulge can stabilize a disk while a diffuse one yields more easily. In a major merger, thin disks are fragile because their order is a delicate balance maintained over billions of orbits. Stars in a disk share a preferred plane and a preferred direction, so small kicks add up into lasting thickness. A spiral's elegance is therefore not just visual, it is dynamical, an organized rotation that can be unmade by repeated gravitational jolts. The disk is like a carefully tuned instrument, where coherence is the point, and noise accumulates faster than intuition expects. When two similar mass galaxies interpenetrate, the gravitational potential changes fast and repeatedly, and the changes are not gentle. The system is no longer close to equilibrium, so energy and angular momentum are redistributed across the stellar population. That time-varying field scrambles stellar energies and directions through violent relaxation, pushing ordered rotation toward random motion. The key is speed, because the potential varies on roughly an orbital timescale, leaving stars no time to adiabatically adjust. Violent relaxation is not a collision between stars, and it is not a gas shock, even though both can happen elsewhere in the merger. It is a rapid reshaping of the overall gravitational field, so stellar orbits are relabeled while the system tries to settle. The phrase was formalized in the 20th century, when theorists realized that a changing potential can thermalize a stellar system without direct star-star contact. Lyndon Bell's insight gave a name to a counterintuitive truth. Gravity can mix a galaxy as efficiently as a physical collision if the background changes quickly enough. A disk star that once moved in a nearly circular path can be thrown onto an eccentric, tilted orbit, as if the floor beneath it suddenly rotated. Multiply that by hundreds of billions of stars, and the remnant's light becomes rounder and smoother. The sharp contrast between arm and interarm fades, replaced by a more uniform brightness profile that declines with radius like a softened spotlight. In some remnants, the inner light can follow a steep, concentrated profile, while the outer envelope spreads into a faint, extended glow. This is kinematic heating in its most consequential form, and it is as physical as a temperature rise. The system shifts from rotation-supported to pressure-supported, meaning random speeds matter more than coherent spin. In plain terms, the stars stop moving together and start moving like a crowd, still bound, but no longer marching in step. That crowd still has patterns, yet the patterns are statistical, not architectural, and the galaxy's shape becomes the visible average of countless scrambled trajectories. Rotation support is simple in concept, and it is why disks can be thin. In a spiral, most stars share a common direction, so their ordered motion balances gravity and keeps them in a flattened plane. Pressure support is different, because stars move in many directions and their dispersion holds the system up. That dispersion is not heat in the usual sense, but it plays the same stabilizing role against collapse. The analogy is imperfect, yet it is useful. Random motion acts like pressure in the genes equations, the bookkeeping that links gravity to observed structure. Observers measure this with spectra that split and broaden, turning starlight into a dynamical readout. A rotating disk shows a clear velocity gradient across the galaxy, with one side red-shifted and the other blue-shifted. A hot spheroid shows less organized rotation and broader lines from higher dispersion. The difference is audible in the data, like a clean note compared to a chord of many frequencies. Modern integral field spectroscopy makes this especially vivid, because it paints a two-dimensional velocity field where order and disorder become visible at a glance. Major mergers therefore build spheroids and can create elliptical galaxies, especially when gas is scarce and cannot easily reassemble into a disk. The remnant often has a steep central concentration from inflow and starburst growth, plus an extended envelope from flung-out stars. Those outer stars can form a diffuse halo of light, visible only when images are stretched to reveal the faintest structures. In the most dramatic cases, the sky around the remnant looks dusted with ghostly arcs, as if the galaxy is shedding a translucent skin. Yet even in a major merger, the outcome is not guaranteed to be a dead, red elliptical, because gas changes the script. Gas can cool, dissipate energy, and settle into new order, unlike stars that conserve their orbital energies more stubbornly. In hydrodynamic simulations, the gas behaves like a fluid with memory of shocks, radiative losses, and pressure, processes that let it shed chaos and regain coherence. Where stars are ballistic, gas is negotiable, and that difference can decide whether the remnant is reborn or locked into quiet decline. If enough cold gas survives the starburst and feedback, it can reform a rotating component that gradually becomes a disk. If fresh gas is later accreted from the halo or cosmic web, a new disk can grow after the chaos. The timescale can be long, because cooling and accretion are slow, compared with the violent, brief peak of the merger itself. In practice, the remnant can spend a long interval looking like a spheroid with a faint settling gas layer, an in-between state that surveys sometimes classified differently depending on depth. Disk regrowth depends on angular momentum, because a disk is an angular momentum storage device as much as it is a luminous shape. Gas that keeps or gains angular momentum can spread into a thin plane, building an exponential disk as it settles. Gas that loses it falls inward and builds bulge-like structure. The same gravitational torques that drive inflow during the merger therefore decide what is left to rebuild afterward. In a sense, the remnant is a ledger, and angular momentum is the currency that determines which components can exist. This is why some remnants become galaxies, with a prominent bulge and a smoother disk that looks almost polished. The disk exists, but spiral structure is weak because the gas supply is low and the stellar disk has been heated. Without abundant cold gas, the density waves that make arms bright have little fuel for new stars, so the disk becomes a quiet, aging sheet of light. Visually, an S0 can resemble a spiral whose paint has faded, leaving only the underlying geometry, plus a subtle lens-like sheen in the inner regions. In other remnants, spiral structure can return over time if gas fractions are high enough, and the disk becomes dynamically cold again. The new disk forms from cooled, rotating gas, and star formation rebuilds arms that were once erased. In that recovery, the galaxy can look deceptively normal, even though its stars carry the kinematic scars of the earlier upheaval. A rebuilt spiral can therefore be a kind of masquerade. Young blue arms draped over an older, hotter stellar component that remembers the collision. The geometry of the encounter also matters, and it is often the hidden variable behind the same headline result. Prograde mergers, where spins align with the orbit, can preserve more angular momentum in the remnant's outer parts. Retrograde or highly inclined encounters can be more destructive to disk order, because the torques couple differently to the rotating material. Even the impact parameter, how close the first passage is, changes how quickly the system loses energy, and how strongly bars and tidal features are excited. A near miss can pull out enormous tails without immediate coalescence, while a deep plunge can trigger rapid inflow and a faster collapse into a single nucleus. Minor mergers tell a subtler story, but they happen more often, and their cumulative effect can be profound. A small satellite can plunge through a disk, stirring it like a repeated hammer tap that never quite stops. The disk thickens, warps, and grows a stellar halo without fully losing its identity. Over cosmic time, many small impacts can do what one large impact might, only more slowly and with more surviving structure. This gradualism is one reason galaxies can look stable in a single snapshot, while still being shaped by a long history of small disturbances. The satellite's stars are stripped into streams and shells, leaving long-lived debris that maps the orbit like chalk on a blackboard. In wide-field images, these streams can appear as faint ribbons wrapping around the galaxy, sometimes crossing themselves in delicate loops. The primary's disk survives, but its thin component is heated into a thicker one, and its outskirts can be flared. A warp can persist for billions of years, because the outer disk responds sluggishly to disturbances. In the right light, the disk's edge looks slightly lifted, as if the galaxy were a vinyl record gently bent by an unseen hand. Minor mergers also build stellar halos by depositing stars at large radii, where orbital periods are long and mixing is incomplete. They seed globular clusters and leave coherent streams that can persist for billions of years, because phase mixing is slow in the outskirts. Those outer regions are like a museum of past accretion, where the exhibits have not yet been rearranged by time. When we map these halos in the local group, we are reading a record that is still only partially erased. These streams are not only beautiful relics, they are measurements, and they are measurements of something we cannot otherwise touch. Their shapes and precession encode the gravitational potential they move through, which means they probe the invisible mass that dominates the system. A stream's thickness, its gaps, and its slight twists become a kind of seismograph for the dark halo. Even the rate at which a stream fans out can reveal how lumpy the potential is, because smooth halos preserve coherence longer than strongly perturbed ones. That invisible mass is the dark matter halo, and it has been steering the merger from the beginning, long before the visible disks feel each other's tides. Halos interpenetrate first, deepen the potential, and set how quickly the galaxies lose orbital energy. In simulations, the luminous galaxies are passengers inside much larger structures, small bright islands embedded in vast dim oceans. The luminous collision is what we photograph, but the halo interaction is what sets the stage, because it dominates the gravitational bookkeeping. Dynamical friction is stronger in denser backgrounds, so halo mass and concentration control merger timescales in a very direct way. A massive, concentrated halo produces a stronger gravitational wake, so the orbit decays faster and coalescence comes sooner. The wake is not material in the usual sense, but a density enhancement in the sea of dark matter and stars that tugs backward on the moving galaxy. It is a gravitational drag born from collective response, an echo in the background that pulls on the perturber and bleeds orbital energy into many small motions. Halo structure also affects how much gas a galaxy can keep, which then echoes into the remnant's colour and morphology. A deeper potential well makes it harder for stellar and AGN feedback to expel gas permanently, because the escape speed is higher. A shallower halo allows winds to escape, and can leave the remnant gas poor. In that case, the merger becomes dry, and the remnant has little chance to regrow a thin, star-forming disk. The same feedback event can therefore have different consequences depending on halo depth. One galaxy retains its fuel, while another loses it to intergalactic space. This is where the hidden role of dark matter becomes explicit, and the narrative becomes slightly unsettling. The visible collision is a dance of stars and dust, but the choreography is written by halos that do not shine. We can watch the luminous parts collide, yet the dominant mass is silent, guiding the timing, shaping the orbits, and deciding how deep the final gravitational well will be. It raises a quiet question. If most of a galaxy is invisible, how much of what we call morphology is merely the surface pattern of a deeper, unseen architecture? Halo shape matters too, because halos are not perfectly spherical in simulations, and the deviations are not just technicalities. Triaxiality and substructure change how streams wrap and how satellites sink, altering the pattern of debris in the sky. Even small clumps of dark matter can create gaps and kinks in tidal streams. If those clumps exist in the numbers predicted by LCDM, the stream should carry their signatures like punctures in a ribbon. The challenge is that baryonic structures can also perturb streams, so interpretation requires care, and that care becomes part of the science. So the debris becomes a detector, and the galaxy becomes its own experiment. By mapping stream widths, density variations, and orbital precession, astronomers infer halo flattening and the abundance of subhalos predicted by LCDM. The method is elegant because it uses gravity against itself, letting the halo reveal its shape through the motion it imposes on luminous traces. When a stream deviates from a smooth arc, the deviation is a clue, and the clue points to mass that cannot be seen in any other way. LCDM gives the cosmic context for why mergers happen at all, and why they are not rare accidents. Structure grows hierarchically, meaning small objects collapse first and then merge into larger ones. Galaxies assemble by accreting gas and by swallowing other galaxies. In this picture, a present-day galaxy is not a single creation, but a layered archive of many smaller beginnings. The idea matured alongside modern cosmology, as simulations and surveys converged on the same conclusion. Growth by merging is not an exception, it is the default. In the early universe, densities were higher and typical separations were smaller, so interactions were more frequent and more rapid. That made mergers common, and it made gas fractions higher, so mergers were often brighter and more transformative. The same collision that would be dry today could have been a luminous, dust-enshrouded star factory at high redshift. The universe was younger, but it was also more crowded, and gravity had less empty space to work with. In that crowded era, even a modest encounter could trigger dramatic inflow, because gas was abundant and disks were more turbulent to begin with. This is also why black holes grew rapidly at high redshift, reaching enormous masses surprisingly early in cosmic history. Frequent mergers and abundant gas delivered fuel to galactic centers, while deepening potentials helped retain that fuel long enough to accrete. The central engine does not need a merger every time, but mergers can provide the torques that remove angular momentum from gas and drive it inward. When the inflow succeeds, the nucleus can outshine the entire galaxy, even if only briefly. The result is a universe where quasars appear like beacons, and then vanish, leaving behind massive black holes as quiet fossils of earlier feeding. The remnant galaxy therefore carries two histories at once, and both are legible if you know where to look. Its structure records dynamics and angular momentum transport, telling you how violently the system was stirred. Its chemistry records star formation and gas flows that happened during and after the merger. One history is written in motion, the other in elements. Together they form a cross-check, because a kinematic disturbance should have a chemical counterpart if gas was driven inward and processed into new stars. Chemical evolution is the merger's slow forensic layer, and it is built from the periodic table itself. Inflows bring gas inward, starbursts enrich it, and feedback redistributes metals into the disk, halo, and circumgalactic medium. Massive stars live fast and die young, producing heavy elements and injecting energy through supernovae. Over time, those metals become a tracer of where gas has been and how intensely it formed stars. Even the relative abundances matter, because elements from core collapse supernovae and type Wire supernovae arrive on different timescales, leaving a chemical clock embedded in starlight. Mergers tend to flatten metallicity gradients, because they mix gas across radii, and the mixing is both mechanical and thermal. Gas that was once metal-rich in the center and metal-poor in the outskirts is stirred together by torques, shocks, and fountains. The merger can drive radial inflows that dilute the center with lower metallicity gas, even as the starburst enriches it again. The result is a gradient that becomes shallower, like a steep hill worn down by repeated landslides. If you could color-code the gas by metallicity, you would see the palette smear and blend, as if the galaxy were being stirred with a cosmic spoon. New stars formed during the burst inherit the enriched composition of the compressed gas, and they lock that composition into long-lived atmospheres. Older stars preserve earlier gradients and earlier kinematics, so age and metallicity together become a timeline. In plain terms, the stars remember what the gas was like when they were born, even after the gas has moved on. That memory is imperfect because later mixing blurs it, yet the broad sequence can remain readable for billions of years. Spectra make that timeline readable, and the technique has a long observational lineage. Absorption features constrain stellar ages and metallicities because different elements and temperatures imprint different patterns on the light. Emission lines from gas trace present-day enrichment and reveal whether mixing has erased earlier structure. With spatially resolved spectroscopy, those diagnostics can be mapped across a disturbed remnant, turning a single galaxy into a chemical topographic map. The map is not literal geography, but it functions the same way. Peaks, slopes, and plateaus that hint at where gas flowed and where stars formed most intensely. In post-merger remnants, astronomers look for distinct populations, because mergers often leave layered components rather than a single blended one. A central, younger, metal-rich component can mark the nuclear starburst, where inflow fed rapid formation. A more extended, older population can mark the pre-merger disks and the heated spheroid. Sometimes the remnant contains multiple bursts separated in time, hinting at repeated passages before final coalescence. Those repeated passages matter, because each close approach can trigger a smaller inflow, building a staircase of star formation rather than one clean spike. Kinematics add the second half of the record, and they can confirm what chemistry suggests. A remnant can rotate in its outer parts while being dispersion-dominated in the center, implying partial disk survival or later disk regrowth. Counter-rotating cores can reveal misaligned inflows and complex merger geometry. These features are subtle, but they are hard to fake because they require specific angular momentum histories. When a core spins against its envelope, it is as if the galaxy is admitting, in motion, that it was assembled from parts that arrived with different directions. All of this connects to a larger puzzle in galaxy evolution, and the puzzle is visible even in broad surveys. Why do some galaxies end up as blue spirals with ongoing star formation, while others become red ellipticals with little cold gas? The color difference is not cosmetic, it is a sign of fuel. Blue means young stars and continuing formation, while red often means an aging population and a lack of cold, dense gas. The dividing line is sometimes called the blue cloud and the red sequence, and it is one of the simplest plots in astronomy that still contains a deep mystery. Mergers are one pathway, but not the only one, and the uncertainty is part of the mystery. Major mergers can build ellipticals by destroying disks and consuming or expelling gas, especially when the encounter is gas-poor. Minor mergers can slowly heat disks and build halos, nudging morphology without a clean transformation. Even without a dramatic single event, a galaxy can drift from thin and blue toward thick and quiet. The difficulty is that the same visible endpoint can be reached by different routes, which forces us to read not just shapes, but histories. The halo again sets the boundary conditions, and it does so by controlling temperature and supply. Massive halos can maintain hot atmospheres that prevent cold accretion, making quenching long-lived. Less massive halos allow cooling and replenishment, making disk regrowth more likely. A galaxy can therefore be shaped by what it cannot easily see, whether its surrounding gas can cool, and whether infill can rebuild what a merger disrupted. In this sense, quenching is not only about what happens inside a galaxy, it is also about what its environment allows. This is why the same merger type can yield different outcomes at different epochs, and why simple classifications can mislead. Early gas-rich major mergers can rebuild disks afterward, producing massive spirals that look surprisingly orderly. Late gas-poor major mergers more often leave spheroids that stay quenched. The universe changes its conditions over time, and mergers respond to those conditions like chemical reactions that depend on temperature and pressure. The same physical mechanism can therefore produce rebirth in one era and ruin in another, even when the orbital choreography looks similar. To test these ideas, we need a census across cosmic time, not a few nearby examples chosen because they are easy to study. We need to see mergers when they were common, and we need to measure what is happening inside them, not just their shapes. That requires sensitivity to faint light, resolution in crowded high redshift fields, and access to wavelengths that can pierce dust. It also requires patience because the evidence is subtle, and the universe does not label its stages for us. JWST is built for that job, and it turns distance into a time machine with an almost eerie clarity. At high redshift, we see galaxies as they were billions of years ago, when assembly was fast and dust was thick. The infrared is crucial because young galaxies are often shrouded, and their ultraviolet light is absorbed and re-emitted by dust grains. JWST follows that re-emitted glow back to its source. In the images, the early universe looks crowded and irregular, with clumpy light that hints at turbulence, inflow, and frequent interactions. JWST identifies mergers by disturbed morphologies, multiple nuclei, and asymmetric light distributions that betray tidal forces. It also sees through dust in the infrared, so it can measure star formation that optical surveys miss. In some systems, the visible light looks deceptively calm, while the infrared reveals compact, intense star formation buried behind opaque lanes. The contrast can be striking. An apparently ordinary galaxy in the optical becomes, in the infrared, a bright knotty system with hidden cores and luminous dust. Stellar mass estimates come from infrared light that traces older stars more reliably, because it is less dominated by short-lived blue populations. Star formation rates come from dust reprocessed emission, and recombination lines shifted into JWST's bands. Together they reveal how much growth is happening during merger phases. They also show whether the burst is centralized or spread across tidal features, which hints at how gas is being funneled. When star formation lights up along a tail, it suggests compression and collapse in the debris, while a nuclear concentration implies strong torques and rapid inflow. Spectroscopy is the decisive step because it turns pictures into dynamics and chemistry, and it can separate lookalikes. JWST can map kinematics through emission lines, separating rotation from dispersion even in dusty compact systems. It can also measure metallicities and ionization conditions across disturbed galaxies. Those ionization diagnostics help distinguish starburst-powered emission from AGN-powered emission, which matters when both can coexist. In practice, the line ratios act like fingerprints, revealing whether the gas is excited by young stars, by shocks, or by the hard radiation field near an accreting black hole. With enough targets, those measurements become an evolutionary sequence, and the sequence can be compared to simulation stage by stage. Some systems show early tidal distortion with intact disks and only modest central inflow. Others show overlapped starbursts and dual nuclei, where two cores orbit inside a common envelope of gas and stars. Others show compact remnants with hot kinematics and fading tails, where the last visible debris is dissolving into the background. In the best cases, you can almost feel the timeline. First a tug, then a flare of star formation, then a slow settling into a new shape. This sequence is not a movie of one galaxy, but it is the next best thing, and it is built from statistics. It is many snapshots stitched together by physics, constrained by simulations, and anchored by the statistics of how common each stage is. The method is humbling because it admits what we cannot do, yet it is powerful because the universe repeats itself. If the same stages occur often enough, then the ensemble becomes a narrative. The deeper achievement is conceptual, because it turns a sky full of unrelated objects into a coherent story about how galaxies change. The deeper implication is unsettling and clarifying, because it removes the comfort of uniqueness. What will happen to the Milky Way is not a special case, and not a rare catastrophe. It is a typical chapter in hierarchical assembly, repeated across the universe. The only difference is that we will be inside this one, watching the sky rewrite itself slowly. The night sky becomes not just a view, but a measurement, because we will inhabit the changing gravitational environment, so we return to the personal anchor, because the local group is our nearest laboratory and our most intimate forecast. The Milky Way and Andromeda are already bound, already falling together inside a shared dark matter environment. Their approach is not a straight line, but a gravitational negotiation shaped by mass, momentum, and the drag of dynamical friction. Even now, the motion is written into tiny shifts on the sky. where micro-arc second measurements translate into vast velocities across intergalactic distance. Their halos are the first point of contact even now, because halos extend far beyond visible disks and overlap in the dark. The uncertain details of halo mass and concentration still set the clock, because they control dynamical friction and orbital decay. Small changes in those parameters shift the timeline by billions of years, which is why the forecast comes with careful error bars. In other words, the collision is certain in principle, but the schedule is negotiable in detail, because the negotiation is happening in invisible matter. Current measurements suggest first close passage in roughly 4 to 5 billion years, with final coalescence later after repeated encounters. The exact timing depends on Andromeda's transverse motion, and on the total mass of both halos, which improved astrometry continues to refine. Even the proper motion of Andromeda, tiny on the sky, carries enormous consequences when projected across hundreds of thousands of light-years. A slight sideways component can mean a glancing encounter with long tidal tails, while a more direct approach can mean faster decay and a more immediate transformation. After repeated passages, the likely remnant is an elliptical-like galaxy often nicknamed Milkomeda, a name that sounds playful but describes a serious dynamical outcome. The remnant's light would be smoother than today's spirals, with a larger bulge-like component and a thickened stellar distribution. In simulations, the final object often shows a bright central region and a diffuse outer envelope, while the last tidal tails fade into near invisibility. If you could stand far outside and watch, you would see two grand disks distort into crescents, then into loops, and finally into a single, slowly breathing spheroid. Whether a new disk regrows depends on gas that remains and gas that returns, and the question is still open because it depends on future conditions. If future star formation depletes the reservoirs before the merger, the event may be relatively dry and the remnant more spheroidal. If enough gas survives or is accreted, a disk could reappear over time. The regrowth would be gradual, and the first hints might be a rotating layer of gas that later forms new stars. Even then, the disk would likely be thicker than today's Milky Way, because the merger's heating is not easily undone. The Sun's fate is dynamical, not collisional, and that distinction matters for any human intuition about crashes. Direct stellar collisions remain extraordinarily unlikely, because even in a merger, the average separation between stars is vast. Stars are small targets in a huge volume, and the galaxies pass through each other like ghostly swarms. The danger is not impact, but relocation. Gravity rearranges orbits the way a shifting landscape redirects rivers, and the solar system is one small current in that larger flow. What changes is the Sun's orbit inside a new potential, and the potential will be deeper, more extended, and less disk-like. Simulations show the Sun could be thrown to a larger radius, or into a more eccentric path, or even into the remnant's outer halo. The night sky would transform, but the solar system would mostly keep its internal structure. The constellations would dissolve, replaced by a bright, distorted Andromeda stretching across the heavens like a second Milky Way. Over millions of years, that bright band would bend and shear, and the sky would become a living map of tidal distortion. The existential threats are indirect and still limited, although the imagery invites dramatic speculation. A central starburst or AGN phase could brighten the core, but distance and shielding make severe radiation at the Sun's location unlikely. The larger risk is long-term, as the Sun itself evolves toward a red giant on a similar timescale. In other words, the merger may change our sky before it changes our survival. The unsettling part is not immediate danger, but the reminder that cosmic events and stellar evolution share the same slow clock. The deeper tension is emotional rather than catastrophic, and it comes from scale and inevitability. From inside, the collision would be a slow redefinition of the sky, as Andromeda grows, distorts, and wraps into streams that cross the Milky Way's own band of light. Imagine a night where the familiar pale arc is joined by a second, brighter river of stars. Then imagine that river bending, splitting, and curling over millions of years. What would north mean in a sky where the landmarks are no longer fixed, and where the galaxy itself becomes a moving, evolving structure overhead? From the universe's perspective, it is slow alchemy again, and the alchemy has rules that we can now name. Gravity converts ordered disks into hotter spheroids, gas into stars and winds, and separate halos into one deeper well. Dark matter stays invisible, yet it decides how fast the story unfolds and what shape the ending takes. The question that lingers is almost philosophical. How much of a galaxy's identity is its visible structure, and how much is the unseen scaffold that holds it? When we say a galaxy dies or is reborn, are we describing the stars, the gas, or the halo that quietly persists through every transformation? With the physics assembled, we now run the clock forward, step by step through our own impending collision, and answer what it will feel like from inside. Today, Andromeda is distant, but its dark halo already overlaps ours in silence. That overlap is not a metaphor. It is a real interpenetration of diffuse dark matter, where particles pass through almost without interaction. Over billions of years, gravity tightens the orbit as dynamical friction bleeds energy into stars and dark matter, turning ordered motion into heat-like random motion. Current measurements suggest first close passage in roughly 4 to 5 billion years. The range shifts with halo mass and Andromeda's sideways motion, because small tangential speeds change everything. Even a modest transverse component can delay the first encounter, or alter the geometry enough to reshape the tidal damage. From inside the Milky Way, the sky would not change in days, but in millions of years. Andromeda swells from a smudge to a dominant structure, then stretches as tides pull out arcs. Its bright core grows more obvious first, then the faint outer disk blooms outward like smoke, revealing structure our present sky hides. At first pericenter, both disks warp and flare, and long tidal streams begin writing new constellations. The outer, loosely bound stars respond first, because the tidal field is strongest there. In wide-angle views, those streams look like pale ribbons, curving for tens of thousands of light-years across the dark. The key truth returns from the opening hook. Stars mostly do not collide at all. The emptiness is decisive, so the merger is orbital reshuffling, not a pile-up of suns. Typical separations between stars are so vast that, even in a direct overlap, most trajectories thread through untouched. The solar system's risk is not impact, but relocation inside a changing gravitational potential. Simulations allow the sun to drift inward, outward, or into the remnant's halo. A small nudge repeated over multiple passages can compound, because resonances and tidal torques slowly rewrite the map of stable orbits. What collides first is gas, because gas has pressure, shocks, and radiative cooling. As the galaxies interpenetrate, clouds compress, turbulence rises, and angular momentum drains through torques. Dense molecular regions can be squeezed past critical thresholds, so gravity wins and new clusters ignite behind curtains of dust. After each close passage, inflow can surge toward the inner kiloparsec, then the inner 100 parsecs. The timing can lag the dramatic encounter, because gas needs orbits to lose energy. In the meantime, spiral shocks and bar-like distortions can act like conveyor belts, funneling material inward in stages. Whether this becomes a true starburst depends on how much cold gas remains that far in the future. Depletion, fresh accretion, and feedback history set the fuel gauge, and we cannot forecast them cleanly. We can model the physics, yet the boundary conditions are written by billions of years of unseen inflow and outflow. If gas is plentiful, dusty nuclear star formation can flare in compact episodes during passages and final coalescence. If gas is scarce, the merger is comparatively dry, and the fireworks are muted. Either way, the light that dominates may be infrared, because dust absorbs ultraviolet starlight and re-radiates it as heat. Deep in the cores, the black holes begin their own slow convergence. Sagittarius A and Andromeda's larger black holes sync with their stellar cusps, forming a bound binary. Long before the final pairing, their surrounding star fields are stirred, and the central regions become dynamically scarred by repeated close approaches. Accretion can ignite active phases, sometimes buried behind thick dust that hides optical signatures. The same inflow that feeds the engines also builds the curtain that conceals them. In X-rays and infrared lines, however, the signatures can leak out. Ionized gas, hot dust, and fast outflows that punch channels through the obscuration. As the binary hardens, stars are flung outward in three-body encounters, carving a lower density core. If gas forms a circumbinary disk, torques can help bridge the last separations. The details matter, because the final handoff to gravitational radiation depends on whether stars, gas, or both keep extracting orbital energy. Eventually, gravitational waves take over, carrying away the final orbital energy as an invisible soundtrack. The merger of the black holes is brief in light, but loud in space-time. In principle, the signal would ring across the local group, a ripple that tells us mass and spin with exquisite precision. After the second and third passages, the galaxies finally coalesce on a total timescale of roughly 6 to 10 billion years. The uncertainty again traces back to halo mass and transverse velocity. Each encounter strips orbital energy, and each pass rearranges the mass distribution, so the later stages are shaped by what the earlier stages already broke. The remnant is likely an elliptical-like galaxy in the local group, with a vast stellar halo. Shells, streams, and faint arcs persist as long-lived fossils of the encounter geometry. In deep exposures, those features read like tree rings, preserving the timing and direction of the original impacts. A new disk could regrow only if enough gas survives, or arrives later with angular momentum. Otherwise, the system settles into a hot, pressure-supported spheroid that slowly fades. The stellar motions become more randomized, and the clean rotational pattern of a spiral gives way to a thicker, more isotropic swarm. Satellites are not spectators, and their orbits are reshuffled as the potential changes. Some are captured deeper, some are stripped, and a few may be ejected by gravitational slingshots. In the background, their own dark subhalos add small perturbations, subtle but persistent, to the evolving tidal field. Now we answer the central question directly, because the collision's logic is consistent across scales. Stars mostly pass by, gas collides and ignites, gravity sculpts tides and funnels matter inward, feedback regulates the blaze, dark matter choreographs the dance, and black holes may merge, leaving a new galaxy behind. And then the story turns back to the present, because we cannot watch our own merger unfold. We learn by stitching snapshots of other collisions into a sequence, then testing that sequence against simulations. This approach has a history, from early photographic atlases of peculiar galaxies to modern numerical experiments that replay the same physics with different initial conditions. JWST is changing the evidence, because it sees through dust to the buried starbursts and dual nuclei we used to miss. Its spectra measure inflow, outflow, and excitation, tightening the physics behind our forecast. When we map warm molecular gas and obscured star formation, we are effectively watching our future, but at many distances and many epochs. What remains unknown is not whether gravity will finish the job, but how much gas will be there to transform it. The universe keeps that variable hidden inside future accretion and future feedback. The unsettling question is simple. Will the merger be a luminous rebirth, or a quieter rearrangement written mostly in stellar orbits? The deeper conclusion is unsettling and hopeful at once. Collisions are not cosmic accidents, but a creative principle. JWST is revealing the earliest drafts of that story, written in dust, dark matter, and time. We began with a paradox. Galaxies can pass through one another, yet gravity still tears them apart and remakes them over time. Across every chapter, the pattern held, collisionless stars and dark matter keep moving, while gas and dust feel pressure, shock, and cooling, turning quiet overlap into luminous change. Tides stretch disks into bridges, tails and shells, torques steal angular momentum, and dynamical friction drains orbital energy until two spirals become one remnant. Where the debris looks like delicate calligraphy, it is really fossilized motion, a record of pericenter passages, resonances, and the geometry of the encounter. In the overlap seams, cold clouds collide first, turbulence blooms, chemistry shifts, and star formation surges, often hidden behind dust that only infrared eyes can pierce. The same inflows that build starbursts can also feed central black holes, sometimes lighting dual nuclei, sometimes burying them behind Compton-thick veils, until feedback sculpts the gas again. And through it all, the dark matter halo, silent, dominant, and nearly invisible, sets the choreography, deepening the potential, shaping the tails, and deciding how quickly the dance tightens. JWST changes what evidence even means, because it lets us read the merger story where it is most obscured, in dust-wrapped clusters, warm molecular lines, and the faint signatures of hidden accretion. The future local group is not a special case, it is simply the nearest chapter of a universal script we now know how to interpret. Andromeda's halo already overlaps ours, and over the next 4 to 5 billion years the first close passage will warp both disks, pull out pale stellar ribbons, and begin the long spiral inward. After that, repeated swings, separated by billions of years, will deepen the damage, drive fresh waves of inflow, and steadily erase the clean symmetry we call a spiral. Whether the encounter becomes a spectacular starburst or a modest flare depends on a single fragile ingredient: how much cold gas remains, how much is replenished, and how strongly feedback has already thinned the supply. In the end, in roughly 6 to 10 billion years, the cores will coalesce, the black holes will likely form a binary and merge, and the remnant we call Milky Way will settle into a rounder, hotter structure. Yet even that ending is not final, because if enough angular momentum-rich gas survives, or arrives later from the cosmic web, a new disk can regrow, and a spiral can reappear like a memory returning. We also learned why astronomers can reconstruct a billion-year tail from a handful of frames, because tidal tails, shell caustics, broadened lines, and buried infrared knots are not decoration. They are constraints. The shapes of streams encode the orbit, the timing, and the halo that guided them, while the ratio of starburst to AGN power can be teased apart with diagnostics that dust cannot easily counterfeit. Better astrometry will tighten Andromeda's transverse motion, stream mapping will refine halo masses and triaxiality, and each improvement narrows the range of futures we can honestly predict. In that sense, the merger is already happening in our equations, our simulations, and our sky surveys, long before it happens in the sky above Earth. So, when the Milky Way meets Andromeda, what survives the collision? Our stars, our sky, our black hole, or the story we tell ourselves about home? The answer is that stars mostly survive as individuals, but not as a familiar city of orbits, because gravity rewrites their paths while gas collides first and decides where new light will be born. Our black hole likely survives too, but not alone, and the sky survives only as change, because home in a galaxy is less a place than a trajectory through a shifting gravitational field. If galaxy collisions feel like destruction, it is because we are watching order being dismantled at one scale so it can be rebuilt at another. In the slow alchemy of gravity and gas, revealed through dust and deep time, the universe reminds us that identity is not a shape you keep, but a pattern you pass on. If you want to follow that pattern as it sharpens, look at the faint streams around nearby galaxies, and at JWST's hidden mergers, because they are our future written in someone else's past. So, when the Milky Way meets Andromeda, what survives the collision? Our stars, our sky, our black hole, or the story we tell ourselves about home? The answer is that stars mostly survive as individuals, but not as a familiar city of orbits, because gravity rewrites their paths while gas collides first and decides when new light will be born. If galaxy collisions feel like destruction, it is because we are watching order being dismantled at one scale so it can be rebuilt at another. In the slow alchemy of gravity and gas, revealed through dust and deep time, the universe reminds us that identity is not a shape you keep, but a pattern you pass on. If you want to follow that pattern as it sharpens, look at the faint streams around nearby galaxies, and at JWST's hidden mergers, because they are our future written in someone else's past.